We are Payload Lander. I'm Aubrey.
I'm Lane.
I'm Matt.
Wow, you guys are really loud. Okay. Doc, over here.
Okay, so for the first change that we made, we just edited up the L channel slightly to fit easier in the 5-inch diameter. So we added a counter bore in the machining process, which is going to give us about 0.2 centimeters.
That was for the screws.
Okay. I wasn't sure what that, but it gives us some tolerance basically, which was an important improvement from last year.
So this is a screenshot from the IREC rules and regulations. You can see that it's plus or minus 2 millimeters length and width, which gives us 10 centimeters in the U plus or minus 0.2 centimeters for tolerance. Additionally, with the chamfer that we've added, which it's kind of hard to see, but it's there. It gives us an extra 0.032 centimeters on each side, which gives us 0.064 centimeters of clearance on total, like each side. That made sense. Yep. And then the screws that obviously you can't see here, but we are going to use 632 counter bores for to attach the L channels to the plates and the cross members and all that stuff. Yeah.
So assuming we don't change anything else, the plate to plate of the accuracy section is going to be 9 centimeters and the paddle height is going to be 7 centimeters, just slightly less than last year.
Yeah. Or a little more than last year because of the higher servos or the bigger servos.
So machining,
No.
Oh, sorry. In terms of general gear setup, using 3D printing gears, places are also 3D printed this year. A 1/4-inch hex bore, and our belt length is 6.632 inches, which is a bit less than that. It was the same as last year.
This is you just using the belt calculator.
Cool.
We have a 45 tooth for the center pulley, and a 16 tooth for the ones that are attached to the servos on that hex. So the smaller ones are technically going to be the timing ones, which will have a belt that'll move the center ones, if that makes sense. Yeah. Cool. And then machining, I would have machined something to show you. However, it's been a month and Washburn hasn't responded to my email. So I followed up, but they still haven't, but that's okay. Just the number of operations. L channels are going to end up being, assuming similar to last year, we're going to do 2 ops with 1/16 inch standoffs, not standoffs. Are they called I don't know. Whatever the plate things are that raise it. Thickness so that we can make sure we can drill our holes with enough clearance and not hit the vices. And then the plates, similar to last year as well, as we're going to need 5 ops this time because we need 1 for each side, so we can rotate it and get the height we need. And then we'll also need 1 to get the blind holes, which you can see in the top plate is for the bearings and some of the like placeholders, and then it'll be for placeholders in the other one as well as the through holes or the through spacing for the servos. That's literally it.
Thanks.
I didn't want to do it way faster. I'm assuming there are questions.
Yeah.
Okay.
So first one, let's just start on the side three, because I think that's easiest.
This 3? No, that's 4. 3.
So for the cutoff for your out channels, I assume you buy them as out channels. You usually have.
We have bought them, and it's not L channels. It is rectangular prismatic stock.
So I know you said that Washburn has talked to you. By the way, talk to me. If I work there, I'll get you in.
Okay.
Like, what's your plan for manufacturing?
Just probably using,
Mill.
yeah, mill with step down, just to get like the first side. So if you're looking at this, do I have a laser pointer?
So like, how are you planning
Yeah, I
it
don't.
into machine?
So it'll just be clamped regularly as like with the thickness of the bottom will be at least what's showing. At least like what's clamped in the vise, and then we'll mill down to that, if that makes sense. They'll be 40 centimeters, so we have to use a double vise.
And you've done,
Did it last year.
and it has enough. You have enough depth in the vice shop. The corner, that corner on the left-hand side of the
Yes.
bell panel, it comes down pretty far though.
That part is gonna be machined when we have to, so we have to like flip it.
2 ops.
Yes.
The other question I have about machining is on slide 6. So you talked about machining the plates in here, the
Correct.
gray. How are you planning on machining the corners there?
So the way we did it last year and the way that worked last year is you put the plate, actually it's gonna be more than 5 ops. So you put the holes you need in the top and or bottom first, so the through holes and the blind holes. And then instead of having it like flat this way, you have to turn it up and then like each side. If that makes sense, and it'll just be a mill, like you mill out the corners. Does that make any sense?
So
No, no.
you can't mill a corner a 90-degree angle. How are you machining a 90-degree?
Vertically. So like if the plate, this, how do I arrange this? Do I,
How's
Oh.
machining?
just one of the mills? Yeah,
I'm really curious.
vertically, like, you know how, because they have, the mills have, yeah, if it comes straight down, then it can have a 90-degree. Yeah.
Okay.
Oh, yeah, not technically a perfect 90. It's,
No.
a square end mill?
So like regular milk
Is-
has sort of camber at the end.
Yes, yeah, we used a square one. Yes. Correct. Sorry if that was confusing. We do know it wasn't. That made sense.
My last question was for slide 5, which is the 3D printing, just to make sure we know what material we're using on the side.
Most likely we'll run some more tests depending on strength. I don't think there'll be any reason to not use PETG, but we'll either use PETG or ABS. We'll default to PETG, but if there's a problem, we will go to ABS.
So safety.
Yeah. I think it was, yeah. Did you have a question?
Yeah, I have 2 questions.
Okay.
First, back on slide 6. The angle that I thought Ken was talking about.
Mhm.
Are you aware that you have internal 90-degree angle?
Yeah, those aren't gonna be full 90 degrees. The servos aren't full 90 degrees. Was,
Internal 90-degree.
oh, that makes more sense. That's not what I thought you were talking about.
No.
I thought you were talking about where the L channels are.
No.
Yes.
In the internal.
No, yeah, those aren't gonna need to be perfect 90 degrees because the servos have, like, space.
Last exact cap.
Correct.
What is the angle? Do you know what angle you need to between?
No, but I'm gonna figure that out once I can, yes.
Yeah.
And I'll probably be working on cam mostly over break. And then doing it. That made sense. No, it didn't. Yes, Amber.
When you're talking about plus or minus 2 millimeters, that's how I'm referring. Just to clarify, you're talking about the cube set tolerance, not the tolerance with the chamber.
Correct.
Hearing it is the other way.
No, so the tolerance that we have of 2 millimeters is the tolerance that we have per IREC. So, and I was just using that to explain that with the amount we will be taking off will still be in that tolerance for IREC.
Okay, so that, unless you're going to chamber the side, sure. That tolerance, because you should be. That's a they will tear.
Okay,
But if there's a little chamber, they're not gonna tear. So you can make that chamber bigger right?
Okay.
A bigger tolerance, which would be very cool. Because with that chamber, it will end up taking. Definitely.
okay,
So I was looking at the. Seven issue, but the test launch, we still had the issue about it, so I think part of it is just putting more that. I think there's just loaded more bigger. Try to shut it.
That's
So just something to know, like I do think this will help for the climate rocket, but like 6-inch rockets still have issues, trying to get in.
okay,
And so I think we just need that, when they want that.
okay.
In the line of where it goes down. So. Yeah.
Thank you.
Your other question.
Yes, the other question, can you go to slide 5?
Yes.
Can you tell me more about those, shaft extensions you have on the servos? Are those off the shelf parts or is that something?
The yellow that you can see here, those are cots that we're just gonna cut down because they're a little too, the way they come, they're plastic. But it's just basically what it is. It's a 25 tooth spline, which is the servo spline that the servos we have are. And then it's an adapter to a hex shaft. So they're just gonna be cut down so that we have the space to put the hex shaft. And it doesn't, because the way they come, I believe I want to say like a 1/2 inch to 1 inch from the bottom of the, like, you can't see where I'm pointing, the bottom of the like spline which here is the top, like bigger part to where technically the bottom of the hex is. But we're just going to cut it with like a hacksaw or something. It's not going to need to be super precise, just so it takes up less space, but
Yeah.
still hex.
Yeah, I was just worried that the slide mentioned 3D printing.
No, yeah, that's not going to be 3D printed. Yeah, that's going to be bought from Rev Robotics. You had more questions, yes.
One little one, for the arms that are opening,
Yes.
are you planning on machine?
They were printed last year. I see no reason to machine them unless we find a reason to machine them. Okay. Mm-hmm. Yeah. We'll probably, right now, it's just the CAD. I haven't totally put all the tolerances in. There are some. The tolerance we'll probably end up using is probably, I'm not gonna use, probably somewhere near 0.5 millimeter, if I had to guess. Yeah, okay, yeah,
I mean, they're gonna be bolted down.
that's true.
That's what I was just gonna say is force of like, it'd be held in place by the screws on the classes, right?
Yeah.
Not physically.
They're gonna be held in place by the servo mounts that are in purple.
So those are just.
Yeah,
Just. Structures.
No,
That's what, I just wanna make sure that like, we start, I mean, I think it should be fine, I'm pretty sure both are making it's identical. But, just maybe after CRSI, just maybe.
send a message.
So being like, hey, we need to decide. Just wanna make sure it's still. It does need, it's.
Yeah.
I'm trying to get it. Some sort of.
Yeah.
Well, I was thinking like, maybe that's just good, right now we just go ahead.
Good. Okay. Thanks, guys. Oh,
Yeah.
I wasn't told. I will. I took everything to complete that I have. Yeah. I don't think they released anything. Well, I'm not.
That's good sense of that.
Theoretically, they had MED metric. So that's good. I would say that, yes.
That's.
I would agree.
There,
No, yes.
it has the antenna actuations.
And I will say that. Okay.
That's good one. That's what they thought. Yeah. I think we're.
I feel much better about it.
Very easy interviewing.
Not worried about it.
It's like a company. No, I was gonna say, it actually felt like they got cared about. That's great. They didn't care about it. Like SpaceX symptoms, experiences with it. The relativity was like. It's very hot. He was like, actually was like hockey. It was like, yeah, actually, like your experience. SpaceX, like, an opposite experience. SpaceX. It's like, when I got into the boat, I got solved.
The only.
Yeah.
We were all good.
So like,
Where are you going?
I just kind of see.
Fun.
I don't questionably.
Sure.
like, I wish I did that.
Yeah, but I'm saying, like, that, we could, I can edit mine.
I just saw it, you know, that's around.
We can take like.
I refuse to. Yeah. Is that Bloom? What? The hell is this? Why the hell is that? It looks so. Like, complex. Yeah.
Those things there. Yes.
Is that it?
Yes, now like.
Questions about that?
I do. I don't really care. I didn't see actors and stuff. It's not.
There's no way. There's two rounds of. We're not part of the collection.
We're using my.
So that's what I thought. We both.
Also, like a kind of like has a. I guess you was looking at these. And they can build people who are not just very. Because of that. If I send it in the data discussion. I'll get it. It's also. That. Right at the top. Everything really actual pencil. It's a wire. Big extension, you just go. Yeah, I see, you just submit it. Just on any minute. Because I just don't feel like there's. I don't feel like.
Yeah, what if I just think it's essential the next business?
I just like. It's just.
We have two extensions?
Yeah, I haven't used that yet.
Wait, I'm using my extension.
It's really easy though, like I just don't.
Probably already has. I don't know if we covered it soon. I'm feeling about.
So there's.
It's. Obviously, part of the airport. Let's go.
Yeah. Yeah, I didn't believe the one other.
Like, so I thought it was go again.
Sorry.
So what did we do SLS service? So,
Yes, SLS.
Starship. Actually, it would be SLS and the large and lower stage of this thing.
Yeah, and stationable strap on the side. And talking on the side.
Yeah.
Yeah,
That's all we do.
yeah.
Except for us. Not even. Just like, how can I be boost with you from the spirit? You've never be like. You have these slides.
I saw the fact.
Oh.
Yeah, cross ones.
And then you also have to get the Delta heavy where it lights something higher.
Going through. You get like an urban failure in there too.
Yeah, there you go.
But I checked, when I got the point for the Chinese and digital, I did she doesn't pay so much that there was peace.
A lot of markets are low key. That's pretty where you're doing. That should have launched you like. I decided not to eat it and I said. Feel politically. I think it's better not to. So I was just gonna say, I don't think US salad.
Yeah.
I guess. I can do it. I said that's not nothing by that. But you don't. I'm gonna try to. Yeah, I'm gonna do that.
This is this project.
Teaching.
Yeah, it's a fun idea. Yes, you weren't here. No, sure. Like the.
In 2019.
Application. So if I don't. This was dynamics. I wonder if that's.
Oh, you're right. Restructures and then.
You like. Yeah. Like. You might pick. You can get to. Shape of lost 14 minutes. I mean, we're French. I think it's because I tried to do a. I was just exposure, so I'm I don't know.
So one other thing like this,
No way. We need some of that. We have like everything, so it's just like that's. Really want. Like what? No, I'm walking.
It helps with class.
That's so funny. I didn't tell you about it. That's so. No. It's actually.
You guys also spend a week on this.
She goes back, so it's like, wow. Yeah, she just signed up for the game, so we like, man, keep driving. Wait, you're drinking, man?
Leave your bag.
Wait a second. I'm just gonna give it a fire. Yeah, you saw it. I drove. I drove. That's so weird. No, tell it. It's really snow. I'm shitting. I was like, Rax and John. It's also. It's the same. He goes like this. It does. Mike Chops.
This is the curly one.
Let's see what they want.
It's just like what is this?
Oh, we have one more person. It was here like 30 minutes.
Why is that five? Oh, five. Why is the one? Oh, they're 27 same letters.
So what did
Like, the reason why I think
it's us was they studied for that. Been like having a. Bill.
No, he's.
What are you doing?
They're trying to get a box for me on the hand.
I'm not doing you wrong, this is really curious. I'm just curious.
I also just plain text. Wait, it's right here. This is it. What does it contain? A cube?
Yeah.
This is it. Wait, open it.
Download
You
it.
have to download it and just open it.
It's pretty easy to write STL files in fact.
Technically, any file is a text file. If you can go.
True. I can G code my 3D printer. If I
You can write, you can theoretically write a video file when I'm recording.
Is it on tape now?
What?
I break when
How about a cylinder that launches? Or mesh links are different.
Oh, I don't think they have. Okay, hey, is there anything still?
it's more like with all these printings.
Right, like the guys, looking at the sample.
We can do it.
Yeah, I can just take slides.
Well,
Take all of them? Sure.
Oh, really? They have one person.
Yeah.
You're just gonna take all of them? I can,
Yeah.
until he shows up.
Yeah, until he shows up, and then we can just jump in. And then if he shows up, you can just.
Just a reminder, you guys are standing within the podium here, in order to speak in the class that I'd like to be able to remember what you're talking. Okay?
So this is the two-stage rocket mechanisms. I'm Aiden.
I'm also Aiden.
My name's Pierce.
I'm Tam.
Colin.
So the mechanisms sub-team, we have 3 sub-projects. The air brakes, which creates a controlled drag on the rocket. This year we are doing retractable rail buttons to passively retract the rail buttons after launch. And then we have the avionics bay to house all the electronics and 2 cameras, and they need to be airtight. So first we have the air brakes.
All right, so coming from PDR and the work we've done, we have a few new design requirements. With the air brakes, we want to achieve greater than 50 pounds of drag at the full extension of the flaps. The fins or the flaps must be flush with the outer diameter of the rocket at launch, and also when they're just not extended. They must not compromise the structural integrity of the rocket. So we had talked about before about how the air brakes, and you'll see in the next few slides some pictures of the catting with them, how they are kind of taking a big chunk out of the airframe. We want to make sure that the structural integrity is still sound when that does happen. The fins must not create a moment on the rocket, and they must achieve full actuation in less than a second. So just a quick overview of the structure of the air brakes. We have a little diagram here where the inner airframe tube labeled 1 is just kind of the inner tube that wraps around the individual components inside that are allowing the air brakes to fold open and close. We have the outer airframe tube, which will align with the airframe. We'll have the top and bottom plates, which cover the mechanism on the inside. And then we have the top and bottom couplings, which connect to the other components right above and below the air brakes. Now, the components inside the air brakes themselves, we have the actuating plate, which you can see is labeled 1 in the center. We have the linkage labeled 2, that is between the actuating plate and the flaps. We have the actual flaps themselves labeled 3, and we have the flap plates, which are labeled 4. And we're going to go into what each of those components are in the next few slides. So the actuating plate is this kind of squarish shape here, centered directly in between the flaps, as you can see in the diagram. The lead screw, which has a diameter of 1/4 inch, goes directly through the center of the plate in that big hole you see right in the center. And there also are going to be 4 support beams or rods, which aren't currently shown in this diagram, that extend through the plate in those 4 outer holes around that center hole, making that the big outer holes there, making that square. And this will prevent it from spinning as it goes up and down the lead screw. So the vertical movement of the actuating plate along the lead screw actuates the flaps. So when the motor attached to the lead screw causes the actuating plate to go up, it will close the flaps. And then when it goes down, it will open the flaps. And the curved edges that you see add strength to the actuating plate, actuating plate. So the linkage is kind of the exact piece that pushes and pulls in the flaps. It extends between the actuating plate and the flap plate. And as the actuating plate moves down, you can kind of see how the linkage plate will push the flap out and cause the air brakes to actuate. The length of the linkage is 2.5 inches, and there are shoulder bolts used at revolute joints. Now, the maximum shear force that these joints will experience is 124.8 psi, which is less than the threshold for these joints, so there won't be any issues there. Now, moving on to the flat plates themselves, there's 2 main components of the flat plates that go into one. We have the flap, we'll call the circular piece the flap, and the piece on the inside, the kind of the triangular piece there, the flat plate. That flat plate connects with the linkage in the triangular design of it, as you can see with the numbers there. That triangular design is optimal for maximizing drag, which is one of the big design requirements of the air brakes. The curvature along each of the sides of the flat plate is to prevent the plate from bending, gives it extra strength. The flaps attach with countersunk screws into the threaded holes, and there's a 3D printed spacer between the flap itself and the flat plate. This allows for just easier manufacturability, makes it possible to create this design. And,
So now we're just going to talk about how we did drag force calculations. So we have a MATLAB script that uses 2 approximations. The area used in our drag calculations is just the projection of the flap in the XY plane. And then the coefficient of drag scales with sine squared. And so you can see in the bottom right, just the equations that we used. The linkages are shown above. And then we're assuming the force is acting perpendicular to that green linkage, which is the flap. And that force is being used to simulate all of the forces on each joint. And that'll allow us to determine what the power we need of a servo is, and if our linkages will be strong enough to withstand the forces.
And just to note, the triangle on the right of the screen is a rigid body, not multiple linkages. So for the motor and lead screw specs, we have not spec'd a motor and lead screw yet, but so based on some calculations of the length of what the lead screw would need to be and the diameter, determined that the critical speed of that the lead screw can spin before it's called vibrating before it hits critical vibrations is super high. So we're more limited by the motor and servo at 6 volts. And then so assuming a 0.5 inch per revolution lead screw, which is somewhat high. Realistically, we might need a slightly lower one. With that lead screw for a 0.5 second actuation time, we would need the motor to spin at around 600 RPM, and it would apply about a 6 pound-inch force on that motor. And then, so the air brake system has a inner coupling airframe tube, and then it also has the outer airframe tube. And they both, we've just mocked up one of the coupling tubes from structures. It's a very slight modification. The flange just moves down slightly, and then those two airframe tubes sit on either side of the coupling. And then they both would be attached with the same radial bolts. We would epoxy a nut on the inside of the inner tube and bolt through all 3 of those plates. This shouldn't change any of the structure's calculations or designs all that much. The reason we have the 2 tubes is because they both have quite large holes cut in them. Yeah, so avionics bay.
Next up for the AV bay, this is our current design, a pretty significant difference from PDR. So we switched over from a stack design to a sled based design. It houses all the electronic components, so the boards, the 2 cameras, the live video transmitter, the camera boards, the GPS, and then currently we have 6 650 batteries, but that can be changed depending on the air brakes. So this is the CAD drawing for a side view. You can see all the height distribution. So the bottom part, we have the cameras, the camera boards, and batteries. That middle section houses the flight computer, the LVT, and GPS. And then the top section is the circular helix antennas. So there's a dedicated space of 11 inches for the AV bay, and this is about 10.5 inches, not including that top part. For the camera, we have the outward facing mount, which is based off the mount from the 30K rocket. Moving forward, we are going to look into a unique mount, which is an idea of having a 2-piece plate clamp from the inside and outside of the airframe. And then the downward facing camera, you can see the acrylic insert at the bottom there to keep it airtight from the air brakes. And here's the CAD drawings from the bottom view. So the acrylic insert, that 1/4 inch hole is for the camera. We have the little 1/4 inch hole looks random, but that's for the pass through for the air brakes, and then those 4 other ones are the structural rods. So for materials, first off, the structural rods, we're looking for a strong, lightweight rod that has minimum temperature deformation. So we're thinking of aluminum or another type of metal. For the bushings that will sit in between the sleds and the actual rods, we were thinking about a 3D printed nylon, which is still flexible like TPU, but has a much higher temperature rating, so it won't deform like I've heard from last year. The sleds and rod spacers themselves, another high temperature rating plastic. I looked into this plastic called Peak, which is 3D printable and has a much higher temperature rating than TPU or any other common 3D printing materials. The support bulkheads that are not on the bottom or the top, the 2 in the middle, we're looking for another lightweight material, possibly a carbon fiber plate similar to what you would find on a quadcopter, and then just that acrylic insert at the bottom. And then moving forward, finalize that mount for the outward facing camera. If we need, we can fit up to 4 more batteries at the bottom, depending on the camera runtime, as well as the air brakes. And then we need to finalize research and materials, including the plastics, approval from EnP, and then begin the manufacturing process.
Now we're going to move on to retractable rail buttons. So for some design requirements, they had to interface with the standard 1515 launch rail. They needed to retract, which caused minimal friction during the launch. The button hopefully would be flush with the outside of the rocket after launch. We wanted a passive retraction method to reduce weight and need from electronics. And then the retraction mechanism occupies as small of a radius as possible inside of the rocket. We looked at a button design from 2 years ago, and we decided this would be a good starting point and improve that from here on out. So it was a fairly simple design. The compression spring pushes on these 2 tabs down on that blue piece on the bottom, and that would push the button down, and the black piece is a Delrin button that we would manufacture. This requires fairly tight tolerances to make sure it doesn't get jammed and to make sure we have good smooth motion and friction, and it would be mounted directly on the inside of the rocket tube. So the top of the blue piece, the guide, would be mounted on the inside, so the button does stick out a little bit so it is flush. The button guide, again, has that outer radius that is flush with the rocket, and then it has slots along the side to reduce jams and failures. And there's a step on that hole on the top of the guide that helps make sure the button doesn't go too far in and it's at the right height to be flush. Now for the rail button itself, we chose to do a Delrin cap because it has a low friction coefficient and it's an easy material to machine. On the cap, we want to countersink. So the screw will be flush and it's made to fit a 1515 launch rail. Then we'll have an aluminum body. It has the guide rails to prevent rotation. And then there'll be a center hole, which will be tapped for the screw to attach to. And then we'll have a screw that goes through and screws into the aluminum body, which we still need to spec out. Then for tolerances, for -10 degrees Fahrenheit, the Delrin contracts 2.215 thousandths of an inch more than the aluminum. And then for 120 degrees Fahrenheit, Delrin expands 4.756 thousandths of an inch more than aluminum. That means there must be a gap of at least 5 thousandths of an inch between the diameter of the guide hole and the rail button. So assuming a manufacturing tolerance of plus or minus 1,000th of an inch, this would create a maximum difference in diameter of 9.5 thousandths of an inch between the Delrin and aluminum diameters. That said, the aluminum part of the rail button will have a much smaller maximum difference of 5 thousandths of an inch, which will help offset this. Then we have an arming mechanism for the rail button. It'll just be 3D printed, most likely in ABS or PLA. It has teeth, so it slides into the 1515 launch rail and creates a smooth transition. It has a radius on it to allow the arming mechanism to sit flush against the rocket outer diameter, which this is important to note. In the top right photo, the arming mechanism won't actually sit against the row button guide. It'll sit against the outer diameter of the rocket because the button guide is going to be screwed into the inner diameter of the rocket. And then we'll have a magnet to pull out the button when it's retracted. While we were designing the button, we noticed that on our bottom button piece, we needed to make this tab here very thin to make sure there was room for the spring to fully compress. And we were worried that that might break or encounter issues during actuation. So we calculated that the spring constant that we needed was around 4.77 pound-feet per inch, which is around 10 Newton meters. And we were worried that it would break. So we ran some finite element analysis on it, and we determined that the minimum factor of safety, assuming a 12 Newton spring, was 9.2, and the maximum deflection was 0.04 of a thousandth of an inch. Any questions?
Yeah.
No, each not that. It cannot be should be not do. See it. Oh, so you also think it's the side shooting. Also, I don't know where. The makerspace.
So we haven't really looked into the materials exactly. That was gonna be the next step for the next couple of weeks. We're gonna finalize everything. But okay. Yeah, I wasn't sure with the with like the temperature when it's actually launched. What difference? Okay. It's extreme.
Part of the concern is the material warped last year from the heat of the launch, not the temperatures at IREC.
There's three of them working. Like you see, like there was very odd space up and like. I saw the photos, like question, what did that? You can look at it again. What happened? You can see the points where it actually broke and then. It's like there's like indents and person on the internet. It's not really. Yes.
And then also on the slide, once it's big blue. This is something we can talk more about with the galaxy. It would be very difficult to have the camera. It's similarly in the to the space because the cable.
Okay.
Particularly the connector that's very. So.
I don't know much about the camera, so that's okay. Thank you.
On the slide, just a real quick question. The camera's planning on being like, is it going to be placed outside the airframe or is it staying in the airframe?
Ideally, it would be inside the airframe.
Okay.
Yeah.
I was just thinking if you were going to try to do something like 30K, where it's like outside, that would really mess up the aerodynamics.
Yeah. This is kind of just like a placeholder, almost. Just this little insert at the bottom there to keep it airtight. Yeah.
So, the, kind of backing piece you have there, the link there, that's a machine learning, correct?
Yes,
You mentioned that, that radius there was to, prevent the bending of it. Have you done any analysis to see, how much bending load there actually is and how large that needs to be? My gut feeling is that what you have there is way over now.
yeah, it's a little extreme. The maximum forces on any of the joints are around 16-pound force at the moment. So we have not done any FEAs at the moment. We'll do that before machining, but yeah, the radius is a little extreme.
And can you guys like, so the inner airframe tube, is that a standard, rocketry P10 fiberglass tube or something else?
That I don't know what that is, but my assumption was it would be the same as the outside. Yeah.
Have you identified an off-the-shelf source for a 4.7 diameter? I know separations have spec laminates 4.5, and I was like, it's close, but not quite.
Tubes last year.
The diameter of the inner tube can change.
Okay.
Yeah, it's not important for it to be that diameter.
And the last one, my just died, so I can't get a slide number, but you mentioned the nods to guide the lead screw. Can you clarify where those are exactly in this?
They are, do you see the actuation plate in the middle of the mechanism?
Yeah.
And then here, I'm going to go to this next slide. Do you see these four larger diameter holes that are kind of in the middle of the actuation plate? That's kind of where they're going to be. So they kind of run along the length of the, not along the whole length, but parallel to like the lead screw. And they're kind of there for some more support.
Okay. But those are no, I know previous designs of yours.
They are not structural, no.
Yeah, no.
And also, I would ask, given that it's no longer structural, doesn't the linkage geometry prevent a rotation in that same direction? If it would apply.
Yes, but you don't want horizontal forces in a linkage system. It would just cause unnecessary friction and jamming.
Where?
Oh, that was going to be aluminum.
These ones are machining.
The flaps itself, ideally, well, I was thinking it could be a composite and we just cut the tube into sections. The plates itself would be machined of aluminum. Mm-hmm. Yeah. Yeah, can look into different material options.
Yeah, so we should look into make sure one of the cameras will be the left 2 months that blue board. Still, just got it's
just a small,
regular
okay.
cam.
Okay, that'll give more room anyways.
Yeah, and it'll be cheaper, so.
Yeah.
Then how many batteries are on the board, on this car?
Uh,
That you can add for it. Oh,
there's 6.
There's a lot.
Okay.
Yeah. which I think at the last integration meeting, it was discussed that we need 5. But there's plenty of room for more.
Okay, cool, I just want to make sure.
Yep.
And then the last thing for me is just for the, you talked about the tolerance for the,
Rail button
two.
or
Yeah, rail button. The one thou, okay, we hit one thou a lot in one term, but like kind of hope and dream. So I would maybe try to relax that tolerance a little bit. Unless you're planning on doing some sort of inspection and you're gonna like re-machine it doesn't get the mark. But if you're just planning on putting one and seeing if it works well, and just call it a day, and maybe relax tolerance.
yeah, that's definitely
Yeah.
something we can do.
We can do that.
But basically, I just wanna reiterate that we need, you gotta make sure the camera's ready
Mhm.
soon, because really ideally we want someone to look that over before you start machining things.
I have been thinking about the manufacturability of the parts, and they are all doable with a low number of ops. So
Are you guys all ready for Washburn, have like certifications and everything?
mhm.
Do what she takes before.
Yes, I'm going to be machine certified in like a week too.
Yeah, just make sure it's looks. You know, obviously, just make sure it's. Gonna switch the slide back to the start of your presentation to you.
Oh.
Yeah.
Good job.
There you go. You're the wrong slide.
Oh, I did. That's not here for.
First round. Remember last time got a forward, legs and kick. Stop. That's like usually.
Okay.
The work begins.
I'm fine with it. It's it runs open source like software.
What'd you say? Like what? Yeah.
No, I already said. You didn't want to.
Yeah, picture.
We're doing it first?
Yes.
That's
That's on the table. Aaron, let's look at something. Ask me something. Actually, yeah, it looks so.
I'm actually.
I should roll on the door. What's that? I think
I heard you.
You look great.
You can
Wait,
no,
that's-
not no.
No.
That's an.
Can we give him like one more minute or like? Okay.
Wait, retake the picture.
Yeah. Wait, Laura. Yeah.
Ice cream.
And come all the way, they will all of you were.
Yeah. Wait, take something else.
Stop, take a step out. You, everyone, Noah has to take a step this way. Just like squish on the side.
Yeah.
Step forward. You guys are not always.
They're fine.
So, yeah. Are you guys ready?
Yes.
Just a reminder, you gotta stay kind of like within the podium area in order to be on camera, and I would like to be on camera when you're talking. Alright, ready to go?
Yep. All right. Hi, everyone. We are the Rocket two-stage composite sub-team. This is our CDR presentation. My name is Alex.
I'm Meyer.
I'm Jake.
I'm Noah.
I'm Cole.
I'm Joel. I'm Tom.
I'm Matt.
So just as a quick overview, we will be working with the three sections of the rocket, which are the sustainer, the booster, and the transition to go between. And so we have the nose cone, upper airframe, middle airframe, avionics airframe, the lower airframe, transition, then the body tube, then the upper airframe, and another lower airframe. Something important to note is that the sustainer and the booster vary in diameter by 0.85 inches. So the fins we're going to be using standard rocket fins, trapezoidal shaped with beveled edges. The designs will vary slightly, notably with the height and the sweep angle, where the height will be greater for the booster fins and the sweep angle will be less. And kind of to go over our timeline real quick, during B term, our plan was to manufacture prototypes for the fin bevel jig, conduct material testing, finish molds, and practice fin beveling and making coupons to do the material testing. And so for C term, our plans will be to manufacture and begin abacus analysis and force calculations.
So a large part of what we do on the composites team is analysis of the parts that we plan on manufacturing. We plan on performing finite element analysis of the fin can using abacus. There are many other simulation software that can be used, such as SolidWorks and ANSYS, but they cannot model composite materials as well as abacus can, which is why we're using that software. We plan on performing thermal load, thermal stress, modal, and dynamic analysis of our parts. Thermal load is the analysis of how heat spreads throughout the part. Thermal stress analysis views and studies how these variations in heat create stresses within the part and the effects of this stress. Modal analysis is very important. It determines the natural frequency and the modal shapes of the part. And then dynamic analysis sums up pretty much the stresses that you see from outside forces acting on the part. Fin flutter is very important as it greatly affects the structural integrity of the part. Fin flutter is the phenomenon that fins experience due to outside forces. If the outside forces cause the fins to reach harmonic oscillation, it greatly decreases the structural integrity of the fins. We can counter this by using stronger materials, which reduce the risk of breaking due to harmonic oscillation.
So during B-term, in order to determine material properties for the composite layup that we will be using, we needed to determine a methodology for doing this. And so quickly, if you're unfamiliar, the coordinate directions that are commonly used in composite materials are the 1, 2, and 3 axes, which run with the fiber, transverse to the fiber, and transverse but in the upward or downward direction to the fiber. And so we are most concerned with the modulus of elasticity, the Poisson's ratio, and the shear modulus, which, to reiterate, is very important for preventing fin flutter. And so we will be, this methodology can take 2 forms, with hand calculations or with an iterative process in Abacus, where we can conduct simulations and see how these simulations compare to our real tensile and shear testing results. And with these results, we can determine how the different material properties should change and when they are accurate.
Getting into material testing, we plan on running shear and tensile tests for the materials. We have started manufacturing of composite coupons in both dog bone and V-notch rectangular shapes. These are specific to the individual tests as they help to increase the accuracy and the reliability of the results of these tests. And then, as previously mentioned, we are going to use the data from these tests to ensure that the simulations that we are running are accurate for the composites that we are using.
So envisioning material testing, we practice this term how to manufacture coupons made of composite. We're using the same wet layup process we've been using in other practices. We use a 90-45-90 fiber orientation, and also in the end, we vacuum bag for an even load distribution. Currently, when we're doing by hand, we did rectangular shape coupons, but soon we'll be able to use the water jet. So we'll be able to do dog bone and rectangular V-notch shape coupons. And we want to manufacture coupons because this way we're able to record how much material is being used, because as an goal, we want to make sure that we're not wasting any material.
The first of 2 tests that we plan to conduct was tensile testing, where essentially a machine pulls on the coupon from 2 directions, opposite directions, in line with itself. Because we did not have the optimal coupon shape, we did have some significant error in test 2 and 3 in the bottom 2 coupons, where the fracture point was closer to the edge of the coupon, closer to where it was being clamped. Just like to iterate why the dog bone shape would be ideal. But because we didn't have the machines, we weren't able to do that this term. But the 2 main failure modes that we saw were cohesive and adhesive failure. The former cohesive failure involves basically the epoxy itself failing within itself. And a good sign of a cohesive failure would be being able to see epoxy on both sides of the break. And so that first test is a little bit hard to see, but we had basically delamination between the layers, and there was epoxy on either side of that break. It also corresponds with a higher ultimate strength on the test. The second 2 tests were there were compounding errors involving, like, because the fibers weren't perfectly aligned with the way it was being pulled, but also because it wasn't a dog bone shape and we did have fracture closer where it was being clamped. But we also did see some primarily adhesive failure there, where essentially the bond between the epoxy and the fibers is failing, which would typically fail first and be a weaker ultimate strength. And that's corroborated by the data as well. Looking at the graph itself, the machine is able to measure the forces that's being applied, as well as the elongation or displacement of the coupon. The linear slopes that you can see are almost linear slopes, indicate that it was a primarily elastic deformation, which is where it stretches and the material can still kind of bounce back, as opposed to plastic deformation, where it's irreversible and the material won't bounce back. If there was plastic deformation, you would see a non-linear slope and sort of you'd have a peak and sort of jog down, which is what we don't want. So this is good for a composite and what we expect out of these materials. The peaks themselves represent the ultimate strength. So this is the maximum force that the coupon's able to withstand before fracturing. As I mentioned before, the blue line with the most load was the first test with mostly cohesive failure, which is a little bit stronger. The adhesive failures in test 2 and test 3 indicate that there was some error with the way that the coupons were made or with the way it was set up and because it didn't have the optimal shape. And then the steep drop off that we see at the end after that ultimate tensile load indicates the fracture point, and the fact that it's a steep drop off means that the material failed in a more brittle way, which is what we expect out of a composite like fiberglass. So that was the test was what we expected. The other test that we were unable to conduct this semester because we did not have the necessary machinery was a shear test. So as opposed to a tensile test, when the machine is pulling in line, a shear test, you have the machine pulling on either side of coupon and sort of ripping it in half. We plan to create V-notch coupons, again, to center the stress in a more predictable place so we don't wind up with something like we had with the rectangular coupons. And again, the strain gauge is applied to both sides of the coupon and the specimen is pulled apart. We are looking into getting the proper fixture to mount our coupon to a shear testing machine. And that's something that we're planning on looking into at the start of next term.
Okay, so here's the bevel design that we ended up going with in order to bevel our fins. So basically we have a big 3D printed block, and then we have this rectangular piece is going to be a CNC machined aluminum clamp, and the fin is going to clamp onto the block. It's going to be held at the correct angle for beveling. And then we're going to use the picture at the bottom. That's the side view of the alignment guide. That's how we're going to make sure that our fin is perfectly aligned. And when we move it back and forth across the belt sander, we get even bevel. So of course we'll clamp it with we have got holes there for screws. We clamp it, we align it in the guide, and then we have a belt sander and we have a plate on the belt sander that's perpendicular to the face of the belt sander. And we can rest the block on that plate, move it back and forth against the belt sander. And that's what we're going to be doing to bevel our fins. So some of the pros of this design is it's very effective. We can create an accurate and very small angle. The horizontal motion, back and forth motion, is going to decrease the inconsistencies because the sander is slightly inconsistent by nature, but we're going to be able to mitigate that with that back and forth motion. And when we clamp the fin against this large 3D printed block, we're going to be able to reduce any effects of the warpage of the fin. And of course, it's a simple print design. It's easy to manufacture and easy to fix. A couple of cons we're working through is that manually pushing the block into the belt sander does create some small inconsistencies on the bevel depth. And we currently don't have an automatic way to stop the bevel depth at the correct distance. But we of course can measure that as we go, which is what we plan to do right now. And here's a prototype we printed a prototype that is plywood for the clamp right now, but the end design of course is going to be metal. And that's just some testing that we're doing. We've done a little bit of initial testing with this design and it's working well. And we're going to be continuing down the line doing even more testing and then tackling any additional problems as we get to them, besides that little inconsistency to the depth of the bevel.
All right, up next is our molds. So our goal from the beginning of the season, or not season, but PDR has not changed, where we want to make a custom nose cone and transition for the rocket. To do this, we need molds that can produce the desired shape without any visual flaws for successful integration. And the molds must withstand the manufacturing process to yield that smooth surface finish we need. The first mold is the nose cone mold, where it is a 2-part reusable mold that is built around a 3D printed nose cone plug. To make this, which is the final design we've settled on, is laser cutting plywood support structure and gluing that to the acrylic plate, and then 3D printing the nose cone plug and attaching it to the bottom of the plate. And ultimately at the end, we'd seal and surface prep for manufacturing for it to go smooth.
Okay, here's our transition mold, and it's gonna be manufactured in the exact same way we're doing our nose cone mold. 3D printed piece, that red piece can be 3D printed. Then we've got acrylic structure, the parting plane, and that back plate right there is acrylic, and then we'll have some plywood support structure under that when we do the mold layup. Exactly the same construction technique. Surface finish, get it to a good surface finish. Lay up our mold on top of that, remove the parting plane, flip it over, and lay up the other half of the mold on that other side, pull it apart, and then we've got a mold that we can make our composite transition within. For the procedure, how we're actually going to do that is once we have our plug, the red piece in the previous slide, once we have that to a really good surface finish, we apply a mold release agent so nothing sticks. Then we apply a gel coat, which is just going to give us that initial very nice finish to our mold. Then we're going to smooth any of the sharp corners or edges, because if we don't, then the fabric that we lay up can bridge across those edges like that, right? So to avoid that, we're going to use epoxy and micro balloons and just kind of smooth that transition. Then we just do traditional wet layup with fiberglass and epoxy resin, and that's going to create the actual structure of our mold and strengthen it. We let it cure. We remove the parting plane. We lay up the other side using the exact same techniques, and then pull them both apart, and that's our finished mold. And that is a picture of the nose cone plug right now that's been 3D printed.
Next, I'm going to talk about our manufacturing and assembly processes that we'll be using in the next 2 terms. So for the body tubes, we are going to cut them using a saw with a tube cutting jig that we have in Sagamore at the moment. It's been used in previous years. To do this, we measure lengths using a tape measure, add 2 extra inches on purpose to sand it back and get us the perfect length. And we obtain the ideal level using both a plate and datum, which will allow us to get a near perfect level and check the flatness of the cut of the body tubes that we've done. And that's just an example of what the body tube will look like. Next, we have our fin can alignment procedure. So to start with that, we surface prep the root cores of the fins to attach them. We then mark the location on the body tube where the fin will be going by using a Sharpie, and in the tool holders on a CNC machine, and hand jog the parallel axis to draw a line. We will align the fin using a mark, or using the mark that we made with the Sharpie, using a surface plate and with 1, 2, 3 blocks. And we will then use super glue to tack the fins in place before adding our epoxy, our fillets, layups, and allowing the secure, which we've been practicing throughout these last 2 terms. So it'll be really nice to see the fruits of our labor.
That's all. Do you have any questions?
So the first one is slide 45. Sorry, I realize it's a longer back. Which is, so just to clarify, we've done some testing, but we're doing more testing on a different machine.
So we were planning on doing, initially we were going to do tensile and tear testing on the same machine with different attachments. However, the way that we were going to do it isn't possible with the resources at WPI because it's a 3-layer composite instead of a 2-layer composite. The way that you would do it on the same machine would be just like the 2 layers attached like this, and then the machine would pull it apart. But because it's 3 layers, it doesn't work the same way. So that's why we're planning on manufacturing different shapes coupons so that we can do the V-notch shear test.
Okay, just to be clear, the water jet, have you guys used water? Right, it doesn't have excellent tolerances.
Okay.
So what are your expectations in terms of two things? The first one being tolerances of the coupons that you're making, because I'm gonna be honest, it's terrible.
Okay.
And the second one is, are you worried about any sort of delamination, or are you cutting material? Like, what's the order? Because the edges might have something like using the water jet.
Yeah, so in that case, we could, that's actually a great point. I can look into that and then, over break, and then hopefully figure something out to change our plan for that. Mhm. Yeah, no, we haven't been able to use it yet at all, so.
Okay, so slide 29. Okay, so it seems like the consistency of the bevel, please correct me if I'm wrong, is dependent on the edge there of the alignment guide.
It's more dependent on the skill when you're actually putting on the belt sander. We're able to get it perfectly aligned with the alignment guide.
So just to clarify, if your alignment guide is imperfect, that's going to affect your bevel.
Yes, if the alignment guide is imperfect, it will affect.
So what are the temperatures?
I don't have a specific number, but it's plenty good for, it would be not noticeable by eye. If we were able to get the skill perfect, right? The skill is going to be a much bigger challenge to overcome than the alignment guide. I'd say, to answer your question, the tolerances of the alignment guide are the tolerances of the 3D print, which I don't have an exact number off the top of my head, but because it's using a 3D print and because you press it right up against the 3D print when you clamp it, it's going to just be whatever the tolerances of the 3D prints, stacked together or whatever, different 3D prints you have.
How many pins are we making? Because I assume we're not just making the necessary number.
I think that will depend on our success in the practices. If we get you're saying we're going to make extra because we anticipate errors. Is that what you're asking?
I'm saying, are you making extras because you want to pick the best ones that you make, or are you making the number that you need and just making sure you're careful so that they all happen to you?
That's a good question. I think we haven't decided on that yet, but I'd say that I'd anticipate we're going to make a bit extra, but also that question will be better answered when we have more practice on the actual G10 plates. Because here, when we did a practice, we used plywood. So I think we need more experience with the G10 to see how good our outcome and to figure out how much more we need. And one thing about your previous question about the water jet is I don't think we don't anticipate any delamination. A water jet is pretty standard used in composites industry to cut composites. So right now we don't anticipate that being an issue. Oh, really? And for the tolerance for the water jet, this is just I'd say it more matters the consistency. If we don't have a great tolerance, I don't think that's going to be a huge problem but if we have a very consistent cut, then we're going to have the same measurements, accurate measurements.
It's 2 inches. I just wanted to ask, how sure are we that we can't cut into the saw within tolerance a little less than 2 inches? Because that seems like an excessive amount of sanding.
That's what it is.
It's just arbitrary.
Yeah.
So,
Just overcut.
so I do remember, I don't know about last year actually, but I know that when Noah was the lead of composites, they cut the initial tubes almost exactly level, but still had to sand a lot of time because they put them too long on purpose. So if we're cutting I'm assuming it's 2 inches on either side, total of 4 extra inches, that's hours of sanding that might not be necessary. So is there any way we can technically practice that, see what the tolerance is, and then decide how much we're gonna overcut?
Yes, that would be ideal. Except because like we don't have the body tubes yet. I'm not sure like what we would be able to like do the practice cuts on. Does that answer your question?
Yeah, that's fine. I think maybe we should.
That was, yeah, that was also cool. We did actually, I think. The body, that's a lot.
I believe I started, yeah, some of the body tubes, I think one of them got so long, I made it 2 or 1.5 inches too long. We have, what's it called, like a vertical sander? Yeah, that's what, so you do like, you give it some excess and then you do that and then you do the minor.
That's awesome. The advantage to the hours is not the same long inch, it's the same long. So. Let's make sure. Hey, can I ask you a question?
Do you know what to ask a question?
Sure.
I'll ask it for you.
Is the vacuum pump working?
Not that I know of.
Can we get the vacuum pump working?
I have asked Noah Krishnaswamy if we can use his for like making coupons, and he offered that specifically for the coupons. Are you looking to use it for something else?
When can we get the vacuum? Trying to make a joke.
Oh, we'll say it.
That one.
Oh.
You know the.
Okay.
No. Do you know what that's from? And will you wear a wig? We gotta go. Well, I think you guys. I wasn't gonna ask those questions. I wasn't gonna ask these questions because that was like a joke.
Okay.
I mean, it wasn't a joke. It was more of a question for Matt. But. You want me to ask? Oh. You guys are taking or walking that. Did you understand that?
No.
Village of God. It's never, I knew that. And bring cabbies.
I can put them on the table. Okay.
You guys are teaching that. Physically you.
Specifically.
Let's pull the crowd. Where are you gonna stand for this bus?
Up against the table.
Up against the table.
We have more props. Good things. Good enough.
We found it.
What? This was given to WPI many years ago.
Yeah, but we have entirely
In before then.
Yeah, we were told these ones were from AAA, not from you guys. From SDC.
It's all. Up against the table.
Also, like, a lot.
There's also like.
Yeah. One
Even out the.
Yeah. It's like, so like. Somebody can only do the other side. There's also like.
Yeah, so look over.
Yeah, so. I need this.
This smells a bit.
It's so good. I'll play when we have. It's actually so like I was like.
That's already been.
Man, slide 60 already. We're only like 3 in. That's crazy.
Just say we're.
Whenever you're ready. Wonderful. All right, welcome to Ground Station CDR. Let's do this thing. We had a lot of slides to get through. I know Will had quite the reaction earlier when he saw the number of slides, so hopefully this won't take too long. As an overview, same kind of driving requirements as last time. We want to build a system that will get us 90% or greater reception of all of our data over a 30,000-foot flight. That's quite a challenge, but we got to operate at our high data rate for our telemetry, 15.6 kilobits a second. And we want to support the very large bandwidth of our COTS live video system so we can get video, hopefully all the way to Apogee. We'll see if that happens, but things look well. We're going to interface with the appropriate subteams, so our rocket recovery and our rocket mechanisms for 30K and 2-stage, and then also with the flight computer, so with electronics, which I actually do have listed, wonderful, and with flight software to make sure we actually get our data, get our radio installed, and we have data coming down. We also want to be able to handle interference from other teams, so preferably we're not locked into one frequency band. That would kind of suck if some other team is also like, hey, we're in this frequency band. And then we also want to have like a decent live stream display for the competition so we can compete for the live video award and for the best live telemetry visualization award. Some of the regulations that are pertinent from the DTAG as of the 30th. There's a lot of restrictions in most of the bands we used last year, particularly the 915 megahertz, which is why we are not using the XBs again. They're also very low power and we can't frequency hop, which is so sad, and also no XBs. So for what's relevant for us from the official Ezra Discord, which is basically the DTAG at this point, from Mr. Jim Jarvis himself, we have a 1 watt limit for our 1.25 meter systems, that's our telemetry, and a 5 watt limit, thankfully, for the 23 centimeter systems, which is our live video. Those radio modules themselves, we're using the same e-bytes we talked about at PDR. They work pretty well. We've done some testing on them. They're 2 watt modules, but we're going to be running them at 1 watt for the DTAG. They're installed on a separate board from ours, as electronics we'll talk about tomorrow. And they're us making a step in terms of building the infrastructure towards custom radios in the future. Hopefully next year, but we'll see. This is our overall link budget. So we can see here that -60 dBm is taken from our estimations and our research into custom radio module chips. So at the end of the day, our antennas need to give us about 14 dB of gain. In terms of those actual tests for the modules this year, we did a couple of tests over this term verifying that they do actually live up to their specifications. So they do actually output 1 watt, and it's not quite -147. It's about -110 dBm in terms of actually getting that 90% data rate, but that's still pretty good. This chart here is from an IEEE paper where they did testing on very similar modules. We want to follow this line here, where this gives us our signal noise ratio, and that gives us our probability of having an error rate. We're landing somewhere in there. It's not too bad. We do pretty good. As for live video, we have a 10 watt, 1.2 gigahertz transmitter. A little bit further over the DTAG, but we'll be running it at 5 watts. This ends up being a little bit smaller and a little bit more efficient power-wise than most of the 5 watt transmitters you can buy. So we're going to go with that. It's analog transmission, which means we get a little bit better reception when the signal gets a little weak. You get a little bit more staticky, but you can still pick it out versus a digital system, which is completely go kaput. We've got a lot of testing with live video. We've got a lot of different things here where we've done it both in controlled environments in the Y lab, in the 3rd floor AK, as well as in real world conditions where we would determine that with the receiver we're using, we need about -70 to -65 dBm of received power to get a pretty good signal. We've got quite a bit range over here, -80 dBm. Like you can kind of make out those spaces there, but like not really. -75, you can see a little bit more of the like silhouette of him. -70, we're starting to get color. It's still pretty staticky. -65 gets pretty good. -60 is really good, but -60 ends up being a lot to ask of a system. So we're aiming for about -65. That gives us this link budget right here, where it turns out we need about 22 dB from our antennas, which is quite a tall order to ask. As for timeline for the rest of this year, and to B term, hopefully we can get most of the things ordered post CDR, and then C term, order anything that's left to be ordered, start manufacturing, and then by about mid C term, we can start testing once we've built everything and integrating and tuning. And then D term, more tuning, more integration, more full system testing. Hopefully by the end of C term, we'd have something where we could say, hey, we want to launch tomorrow. Great, we can make that work. I'm now going to pass it over to Finn to talk about the rocket antennas, which have changed a little bit since PDR.
All right, so for rocket antennas, as Nick said, some things have changed since PDR, I think for the better, hopefully. First of all, design refinement just for both live video and for telemetry. For live video, we've done a lot more simulations accounting for the placement of the live video antennas in the rocket and tweaking those antennas so they work best in the circumstances that they are in, as well as for telemetry. That's where the major changes came in. For telemetry, no more coax running down the shock cord, which is, I think, all in all, a very good thing because at the test launch, it was demonstrated that that doesn't necessarily always work out very well. Kind of confirmed our suspicions, although we thought it might have been possible. For 220 telemetry, due to the link budget of that, there's much less gain required than for the live video antennas, which gives us a little bit more flexibility in still making it work without being able to have a large antenna on a lower section of the rocket. Aiming to still do one wrapped antenna around the body, though, for the 2-stage. So we can test higher gain antennas if in the future with custom radio solutions, more gain is needed without having the coax running down the shock cord, though. Yeah. So for live video antenna, plan is still to do a spiral dipole with a reflector. And this goes in the bottom of the recovery bay. It's been placed there since PDR. Done more tweaking to account for some non-ideal things involving the threaded rods that are in the recovery bay. And hopefully with a prototype that we can get on the PCB laser soon, we'll be able to do more tuning for that and then do some final testing once it's actually integrated. And of course, tweak the tuning for that. Here's some of the parameters we've got for the live video antenna. It's about 5.5-ish dBi. It has a half power beam width of around 60 degrees. So that kind of matches the predictions that we had at PDR with a more detailed design. Aiming to still do a little bit more optimization for the bandwidth to make sure that it has good enough SWR to be used. And that's again for the 1.28 gigahertz channel for live video. And as you can see, there's also a vertical radiation pattern there. It's roughly symmetric. For the telemetry antenna, for 2-stage, plan is to do a similar wrap dipole like this, wrapped around the bay, and that aiming again to have around 70-degree half power beam width. And if we can get somewhere around 4 dBi gain, that'd be amazing. That's basically the plan. And that would be, again, copper tape wrapped around with hopefully the paint going on top of that to protect it from any damage that would kind of sacrifice the functionality of the antenna. And then have a PCB feed point at the end of the tube, like in the lower end of that diagram. That's similar to how we would do a wrapped antenna in a future year. So good testing. For 30K telemetry, rather than having the coax down the shock cord and an antenna in the bottom section of the rocket, the plan is to kind of go with what we were thinking for the backup antenna, which is to basically just have a rubber ducky, like a electrically shortened monopole in the recovery bay, because again, we don't need a ton of gain for the link budget. That'll be okay enough. And it most importantly is in the recovery bay with all the other radio electronics. No need for any redundancy, checking if the coax has snapped, anything fancy like that. Much simpler system, hopefully much more reliable, and reduces the amount of failure points that we have in there. And for that, I'll turn it over to Garrett for payload time.
Okay, so for the payload antenna, we're going to be operating at 222 to 225 megahertz when it'll be transmitting using the eByte LoRa module. And the main goals for this were to make it slowable during flight and deployable upon landing. We also want a low wind area so the rover doesn't blow over. And this antenna doesn't need an exceptionally high gain because the rover is going to be a lot closer to the ground station of the rocket. So the design we ended up on was a loaded monopole, which has a omnidirectional gain pattern. It also uses a loading coil at its base to allow it to be shorter than a regular monopole, which would be 33 centimeters, but it would have a hard time fitting within the payload. This design has a height of 19.5 centimeters, with the coil being about 1 centimeter tall, and then it can be easily actuated with a servo and will also require a ground plane of copper on top of the rover to function. Next, we have the receiver antenna.
So here's some additional documentation. You guys can look over in meters. It's very great thing. It's just said. So the first receiver antenna is the telemetry antenna. This is a Yagi. You'll find that on the papers if you're in the front row. Otherwise, you can look at the pictures. This is a Yagi made up of 4 directors, the driver and reflector. The requirements for this antenna were approximately 10 decibels of peak gain. That came from those link budgets we showed earlier, and under 1.5 VSWR. This was chosen to match industry standards, as well as being easy to assemble and pack, which was kind of the primary requirement going into the design of this. Whoops. So for the purpose of assembly, the boom breaks into 2 main segments for transport. The elements will insert into slots in the boom, and then they twist, which locks them into place, and a screw goes in, which goes through them and clamps it so that it can't come back out. There's also an insert that holds the 2 PVC segments of the boom together, which should be long enough to prevent them from flexing relative to each other, as well as it goes through the part where it clamps onto the tracker, which we'll talk about in a second. We're using nylon bolts here in the hopes of preventing interference with the actual antenna performance, as well as nylon nuts. These are all standard ones from McMaster Carr, 3 inches long. And they're the same ones that will be used to mount it to the tracker just to keep all the hardware consistent. The elements themselves will be made of laser cut plywood, 1/2 inch thick. We can get this from the makerspace as they sell big sheets of it. It will then be covered with some sort of copper tape or other conductive material in order to form the actual RF element of it. In the event that we're struggling with the tape staying in place, we may also cover that with an additional material, some sort of clear thing. We've talked about a couple of possibilities, but haven't settled on a final one yet. The nut, as I mentioned, provides a clamping force upwards to prevent rotation about the Z-axis, as that was a concern that was brought up previously. The Z-axis here being the coordinate frame shown on the slides. Basically, it prevents the different elements from turning side to side relative to the antenna boom. For the purposes of interfacing with the tracker, there are 3 of these 3-inch nylon bolts which attach into the tracker mount. At this time, they're not in place, but there will be hexagonal cutouts inside the tracker mount itself that allows us to tighten these down without needing a wrench in place. The shape of the mount also clamps the boom in place so that it can't move with that matched radius. Unfortunately, for the live video antenna, we did have to make some design changes relatively recently, within the last week or so. So I don't have as detailed drawings of it, but we intend to use a COTS reflector, specifically this one, with a modified feed point for the correct frequencies that we're using, as this feed point is for 2.4 gigahertz. Reducing it down to 1.2 gigahertz will slightly reduce the performance of it. This antenna at 2.4 gigahertz is rated for 24 decibels. At 1.2 gigahertz, we calculate that it will give us 18 decibels, which should still be sufficient when used in conjunction with the transmitter antennas developed by Finn. The feed point itself will be a custom solution. You can see here a diagram of what that will look like. This is actually taken from a website online where people do this. So this is the diagram that they provided. So now, speaking of tracking, we'll hand it over to Jacob to talk about tracking and how we're going to mount everything.
So since PDR, we've made some pretty big redesigns. We've made a couple estimates because of that. And so our initial goals say that we have our assembly under 80 pounds, and each separate part would be under 25 pounds each. And our new estimates will have a main assembly being about 20 pounds, and each separate part will be about 5. We also predict that only 1 person will be needed for assembly because of the new design, and all other goals remain unchanged. Our new design focuses on rapid assembly, portability, and optimized center of mass. The entire structure is divided into 3 main subassemblies, that being the collapsible speaker stand, motors, and electronics, and the antennas and elevation structure. And since the antennas take up the most space when fully assembled, they're designed to take up the least space while disassembled. The motor subassembly has been reduced mostly to the fundamental electronics, with gearboxes, sheet metal, and 3D printed parts acting as structure. The large azimuth gear that's been taking up a significant amount of area in the last design has been replaced with a planetary gearbox, which directly drives the azimuth rotation. And a worm gear is used for elevation control, which can't be back driven, which helps resist the wind.
All right, antenna alterations. So the live video unfortunately had to switch to a dish, which is less compact and heavier compared to the Yagi antenna. To accommodate this, we'll keep our previous design, but we'll have some slight changes to the elevation and antenna assembly. As for the electronics, the motors and gears we planned on using originally are plenty sufficient to support a balanced dish, so those will not need to change. For our motor calculations and our motor selection, we chose the NEMA 23 closed loop stepper motor. This was favorable because they are fairly short and they have apt torque curve documentation, which is very important. Torque calculations were done at the required maximum angular velocity with 25% full power, and that resulting output torque of 8 Newton meters, whereas full power output 17 Newton meters. The antenna shouldn't face nearly as much wind resistance compared to last year, and the calculated torque output of 8 Newton meters should be more than enough to counteract the winds. So pack up and assembly. So each individual part, once it's assembled, is light enough to carry in one hand. We use locking pins everywhere we can, which has cut down assembly time significantly. And we also have custom rapid connections as shown here. So we have several dovetail connections that use pins and screws to lock and joint together, which you can see on the CAD render and the 3D prototype. It's very fast to put these together. They have very minimum give, but further testing will be done to ensure connection security. And now for live video.
Okay, there's not much to say here, just a bit of an update of what we talked about during PDR. We're using, for the camera side of live video, we're going to use the RunCam Split 4 for its small size. Again, records or transmits analog and records digital video. Excuse me. And then we have it mounted at roughly a 45-degree angle to try to get an ideal view without sticking out too far. So, and then I'll pass it on to direction finding.
So Gavin unfortunately could not make it to today. He's running his office hours right now. So I'm going to go through this really quickly. There aren't a whole ton of updates. We're still using a correlated interferometry system like we've talked about previously and like we did some work on last year. There were issues with last year that we've been redesigning with our new architecture, which does immediate down conversion. So we're not trying to do all of the comparison at 1.2 gigahertz. We're doing it like a couple megahertz. So it's a lot easier. We've built up some testing PCBs and we got some of those from the PCB laser. There were a couple of issues with them, so we've run them back for another revision. So hopefully either by the end of this term or the very beginning of C term, we will have some component testing. Makes our life a little bit easier. And then through C term, we'll be able to do our final electronics design for that and order those PCBs, get that all set up and tested, calibrated, all that stuff. As for our ground setup stuff, Devin's going to cover a little bit of that.
Okay, so sorry, sickness is killing me. So for the ground communication we're going to have a 20-watt radio at the ground station with a telescoping antenna mast to, improve the quality of improve the reception. And then we're also trying to compact all the different electronics and things into the Pelican case, which you can see over there, to make setup a lot faster and a lot easier once we get to the location at IREC. So next up, we'll have software.
Not too much has changed since PDR. We're still using the same programs, the same frameworks for running our software. Flowchart is still the same. There's been some work done, especially on the middleware. That's more or less completed, and some of the more basic backends. We also notably have some mock-ups of what some of the front ends are going to look like with your wonderful MS Paint style drawing by yours truly. We've got two very nice large views from our different cameras. So one camera that's tracking on the ground on board our tracker, and then a camera view from our live video, as well as you've got altitude on the left and you're sort of where we are in terms of the mission. Okay, we're in boost, we're in coast, we've hit apogee, we've separated, we're under drogue, and then you've got velocity acceleration on the bottom, and then a sort of orientation display down there. the other hope, this one's a little bit rougher, but once the payload gets down and deployed, we can have something that clearly shows what the mission is going on. So we've got an image there on the left that we'd be able to downlink over. You've also got like your motor temperature to show sort of the core thing there. You've got your control inputs, so it's very clear that, hey, we're doing this teleoperated. It's not just like predefined program, we're able to control it. And then the hope is that you have some sort of graphic of the rover. Hopefully it looks a little bit better than whatever this hexbug thing I've drawn is, with displays of the different distance sensors where we'd be able to see, hey, this is something really close, this is something really far. A little early days, but it seems like a pretty fun concept. That way, we're really showing off what all of our various divisions have been doing, especially payload in this case. And with that, hit just about time. Any questions?
So, yeah, the interface you're talking about, I know 8th grade. You don't really have to go back to that, you know what I'm talking about, but the interface between the PVC pipes, how long is that gonna be like relative to length?
The insert?
Yeah.
So right now that insert is 25 centimeters long. Each individual segment is about 1 meter long.
Okay.
So it's about a quarter meter.
Okay, and my only concern is, so, yes, it's gonna add some support. The one thing, so you guys are only mounting this screw onto one side, like, it looks like at least, right, doing one screw with one axis, right?
Yes.
So personally, when I were to do something like this, like, it's still gonna bend on the other axis, so I would at least have a screw on each, at least on 2 axes. Because that is a relatively short, like, compared to like the length to the length of that ratio, like, that is relatively short. I would not be confident that it's not gonna bend just a little bit, especially with PCs often not cut flat. So I just keep that in mind, maybe just having some sort of locking screw just to make sure that it can't rotate at all. Otherwise you're gonna, like, even if it's screwed in like this way, like, sure, that's gonna stop it from doing this motion, but this motion is still gonna be illegal.
Yeah, I anticipate it to be relatively minimal on account of, additionally, there will be, could you go to the next slide, please? There will be, oh, sorry, what was it? Yeah, there will also be this segment here, which will be in place on the other axis at the same location. Mostly this insert exists so that we don't have to rely on the mounting clamp to be the solution for holding them together, because that would be a real pain to assemble. But we'll look into it.
Yes. Yes, we're planning to buy 2 new tripods, one for the active tracker and then another one for that antenna mast.
There are some parts that you can buy online that act as brackets, and those are relatively cheap, and those are what we plan on
You're
using.
planning on buying them, you're not.
Yeah.
See. If you pop some sort of design or some of this, right? You know about them, just like, because I know like that last lesson, all we do is kind of just look at that.
Yeah.
It's like, it's fine, but it doesn't give us any real data of people, so.
Yeah, that's the hope, is that we have a lot of this system, as we said, done by the end of C term. And so we have a fair bit of it ready for February, like especially in terms of the sort of deployment and being able to sort of test the ergonomics of the whole thing so that we're not getting the IREC. And this is the first time we've tried this whole system out together, which was one of the issues with last year, is there was a lot of debugging that week. So the hope is that either between test launches and test launch, hopefully in February, maybe there's one later in the year, and then also full system testing at home, that we don't have a lot of those teething issues we had at IREC last year.
Okay.
Sweet.
Slide. Have you, I think this is for the motors, have you put any thought into like any heat concerns with the motors?
I know last year they were running at, I believe, 100% power most of the time.
Yeah.
Yeah. The way it's built, it shouldn't require as much power. We've done all our torque calculations while it's at 25% power, which it's rated to run at full time. So it should use much less than that most of the time. So I believe it should be good.
And then what is actually controlling the tracker? Is there gonna be like a separate board or is it the top book just sending?
There'll be a line going in from the tracker, which will communicate with an Arduino, which will track the stepper motor drivers.
Okay. It'll be the same kind of setup as last year, where there's like a Polaris board, right?
Really use like a.
Yeah, Mars,
Okay,
Polaris,
whatever.
yeah.
Another question, are we on the transmitter? On the M?
Yes.
They said yes to that?
Without the Discord, without the. There is no per DTAG, there is no regulations on like handheld talk around power limits. That radio is also capable of going down to like 10 watts, which is a very normal handheld radio power level. So it's not a significant concern.
I think it just depends on how they consider transmitters, because this will not be on the rocket.
Yeah.
Right. All of their rules have been for the things that are on the rockets.
Yes.
We are always the reason for new rules.
The only other thing with the Pelican case, my only concern with that, is looking at it, is having everything like right next to each other in a black case.
Yeah, we've talked about this a little bit. There's options between doing sunshade, which will be advantageous anyway when you're gonna end up with a screen in there that you're gonna want to see, and other things. We can very easily take like a can of spray paint and paint this white or tan or something like that. This is what was available very cheaply at the time I got it, and I just have it. I'm just donating it to HPRC. I don't particularly care. We also could, but I have a feeling that like spray paint white, spray paint tan is going to do a lot more for it than a computer fan is, especially because it's going to be like in operation, it will be open because that's how you actually interact with everything. It's not like you're going to close it up. It's going to be a closed thing.
Pulling this down away.
Yeah.
And then slide 105, I just had a very quick comment. Rocket. No, yes, we are.
Huh?
I would prefer not to do Philippi.
It's 30,000. The apogee is 30,000 feet.
Can you put 3 zeros instead of a K?
I can write 1,000 out. Would that make you happier?
No, I want the 3 zeros.
This is a minor thing. We can figure. Sure, we can write out 3 zeros. Well. Okay, this is something we can talk about later, but I believe you still using some sort of distance measurement sensor with like a LiDAR or time of flight. Okay. Okay, we can figure out something else to do with that. I still like the idea of having a graphic that makes it very clear. Maybe that's like what we map the control inputs onto or something, but. Yeah, that would be cool, yeah.
No, you're gonna manufacture the slots that rotate. The slots in the PVC pipe? Yes. If you could go one circuit. Go back one. Yeah, this one.
Oh, there we go. Sorry.
This one.
Yeah.
So it's kind of hard to tell from this diagram, although I think it's a little bit more clear I've made it. Yeah. But what this is it's actually 3 holes drilled with specified sizes. I knew that it was going to be tricky to make any sort of right angled things. So essentially just a drill press. We'll put 3 holes. The way they overlap makes the slot. I should have put a zoomed in view, but I didn't.
No, that's pretty good. You could also, maybe like an ML rocker.
That could also work.
Yeah, or we could.
I still need to look at the tolerances. I plan on doing sensitivity analysis on all of the positioning and such to figure out what a tolerance space looks like, so I can look out what machines are necessary. Hopefully, it's just a drill press and a jig.
Awesome.
Off the slides. There we go. Get our.
Picture.
Yes,
I'll get it. That sounds great. New machine.
Oh, you're picturing?
Another picture?
Dude, where you going?
Another picture.
That's my
Make a funny face. You can do second one stuff.
Why are we not so fantastic?
Oh, there you go. We all pose like that.
Also,
Okay, yeah, this one, this one. Stop.
Well, like me.
Okay, have a go.
I quit. Matt, it was in that.
Actually, it should be just.
The entire thing.
Better. That was the most beautiful edit I've ever seen. I love it.
I love.
All right, you guys can start whenever you're ready.
All right. So this is the composite CDR. The way that this is going to be formatted is I'm going to go over a brief timeline and then kind of an update what we're doing the same, what we're doing different in terms of the more like manufacturing procedures for like the fin can and the body tubes and things like that. And then I'm going to pass it off to the more individual design heavy projects for the other team members to go over. So to start off, this is a just slightly modified version of the timeline that I showcased in PDR. So for what's coming next, or what we did in C-term is prototyping and developing some of our final designs for things like the tail cone mold and the bevel jig, continued practices so that we get our procedures down, and updating those procedures, which again, I will go over in the following slides, just after we learn kind of what works, what doesn't, what we might want to change from previous years. So upcoming in C-term is finishing manufacturing some of these final designs, squaring tubes, beveling fins, manufacturing the tail cone, all the stuff that composites has to do by the end of the year, beginning that as soon as possible, coupons testing potentially, and then by D-term, ideally we're assembling the fin can, integration, painting, all that kind of end of year sort of stuff. So moving on to fin can and body tubes, I kind of lumped these together because it's just a few slides of basic procedure. These are not super in-depth because it's more or less the same procedure that HPRC has kind of always done, but just some highlights. So for layups, we are going to try to manufacture is kind of a strong word, either laser cut or 3D print just a few layers of kind of a template for the layup like shape, because it's kind of a weird geometry. That is annoying to have to stencil out every time. So having one flat object to be a stencil for the layup is something that we're going to be doing. So layups will, as usual, be performed on 2 sections at once. Fins will be surface prepped, 3 layers of fiberglass in that 90-45, 90-degree orientation. That is best to kind of balance out the strengths and weaknesses of the fiberglass mesh. And then the layups, as usual, will be increasing in size slightly as you go first, second, third, to avoid the elimination, to kind of give it more of like one surface instead of 3 different surfaces that are either like stacked right on top of each other and all end at roughly the same spot. So yeah, mixing epoxy, applying the first layup, saturating with epoxy, repeating for the other 3 or for the other 2. Peel, apply, breather, vacuum bag, the usual layup procedure. These are just some extra conveniences. All right. Pin alignment, kind of backtracking here a little bit and just going with previous design. The one in PDR is overly complicated. But yeah, marking fin placement in Washburn using machining rather than doing it by hand to get it absolutely as perfect as possible. Pressing an angle block to the base, we're using a base plate, or sorry, I confused base plate and angle block for a second. Pressing the angle block that we will have the fin either clamped to or just held to, probably clamped unless we have a really weirdly shaped angle block, to the base plate edge. And then just, yeah, super gluing the, I didn't write it here, but surface prepped root port of the fin, and then just super gluing it and pushing it right into the fin can. But that's pretty much usual procedure. This is not CAD that we made this year. This is the old CAD of the current design for like tube cutting jig that we have. So we will be using the same tube cutting jig as per usual. This is kind of a comprehensive list of what worked for us last year. Essentially, there were a lot of different steps we took last year when squaring the body tubes. And a lot of them had to be completely redone because we would use one method and that would not work, and then we'd use another method and that would not work, and then we'd have to completely again square the tubes all over with a third method, and finally that one kind of worked. So sticking with what actually worked last year, a preliminary sort of marking of where to sand our fins to was given by essentially getting a piece of, I know this sounds kind of rudimentary, but getting a piece of parchment paper and wrapping it around the body tube or the coupler tube, and making sure the edges perfectly overlap, so that implies that it's kind of perfectly level. Marking it with Sharpie, and then just checking to make sure it is level, and you can always acetone the Sharpie off and then try it again later if you need to. Using the tube cutting jig and the, I forget the exact word for it, but the kind of saw that we have, cutting with about 1/4 inch of excess. That's what worked for us last year. 1/4 inch of excess because sometimes the saw does not cut at a perfectly straight line. It kind of cuts at an angle. That's also why it has the asterisk there of cutting halfway through, rotating the tube 180 degrees and then cutting the other half of the way through, because the saw does kind of cut at an angle where it gets more into the tube as you go down. So that's to avoid essentially cutting part of it too short. But yeah, the 0.25 inch excess is for that, and also because sometimes the saw does cause a bit of like fracturing in the fiberglass body. And then after that, removing the majority of the excess with an orbital sander, and then just going over it with a hand sander, and then testing the ideally squared surface against an angle block to make sure it is flat / level, because that is also the tool that ended up working best for us last year. Right. Fillets. So this year we'll be trying to see if vacuum chambering the epoxy works. Hypothetically, that should be helpful to avoid like air bubbles showing up in the actual fillet material in the epoxy. Vacuum chambering the fillets. Also, so usually when fillets are performed, as you can see in this photograph, everything that is not going to have the fillet on it is completely taped over. Something worth experimenting with next time we do a fillet practice would be seeing if just before curing, removing the tape might be helpful to avoid giving it like a ridge, where there might it might just come out slightly imperfect and we have a little bit of height at the end there, and that's giving us like an extra surface, an extra place for it to kind of, I will be covered with a layup, but still that's just giving us an extra little bit of imperfection. Whether removing the tape just slightly before the fillet fully cures will help with that without kind of ruining the actual shape of the fillet itself, because again, the epoxy is not fully cured, so that is a risk there and something worth testing out. Because even if that does go wrong, you can still do a layup over top of that, and you're not ruining your materials because you can still practice a layup, and you don't have to like remake another test fin can essentially. And moving on to bevel jig.
So this was a last time design for the bevel jig, and while it was good on paper, realistically it wasn't very feasible, because the sander that it attached to could move forward and back, but also like side to side, so which could lead to manufacturing errors, and also it was like very complex and could lead to more errors and more wider error margin. And also it had like some of the blocks had to be attached to like basically like very impossible situations. So we decided to change that for our design for moving forward. So the new design for the fin bevel jig is that we switched to a circular saw on the side, and this should provide a more stable sawing action, which should lead to less defects in the bevel of the fins. And we also redesigned a bunch of parts so that we don't have to manufacture any parts at like weird angles or anything, and we can have everything at like a right angle. And so the main thing that's gonna keep our bevels at that specific angle is gonna have a height block basically under the platform, which is gonna have it so that it's gonna be at that 7.125 degree angle. And also we're gonna have our fins such that maybe pushed against a wooden base, which would be part acrylic and part wood. And not only that, it's also made out of 3 manufactured parts, which should help us mitigate any errors in manufacturing because it's just less moving parts.
So talking about the tail cone mold, it doesn't take a rocket scientist to figure out that this should be curved and not just a block. But the question is like how exactly much it should be curved. So it can't just be conical because structures has to put stuff in there. And so we decided that we were going to do a like modified an ogive shape. Well, the question is whether or not we're going to do an actual ogive or a slightly modified ogive, which goes like a little bit out. The differences are very slight, and it'll just all depend on what the other subteams need. But in general, it'll be like this general curved shape at the end.
For the tail cone integration, the main issue we had to work with is giving 30K structures as much room as possible to work with. They are currently going between two different designs, a wedding cake design and an aero pack, and both of them are very tight on space. So because of that fact, we have decided to go with an ogive shape, which allows them to have the most room that we can possibly fit, as well as being easier to manufacture and having very good aerodynamics. We are debating if we should add about ½ an inch for a cylindrical start to the ogive shape, but that would again just be to give structures as much room as possible. For our test manufacturing, it worked very well. The only difference is it wasn't exactly a 1-to-1 as we only used 4 layers of fiberglass rather than 6, so it is slightly thinner than what we could expect, but that was simply to save on materials. The production procedure, the screws were successfully protected from epoxy by vacuum tape. However, next time when we do it, we want to put on screw caps because the tape ended up getting pushed into the mold, correct?
Yeah.
I believe that's it.
All right, during the manufacturing procedure, we encountered some issues. For example, the screws poking through the vacuum bag, which we tried to fix by putting vacuum tape on them, but during the vacuum pumping process, the tape got moved, so that didn't work so well. Also, epoxy got everywhere, especially between in the interfaces between the parts of the mold, so they had to be pried apart. And as you can see in that image, there's excess fiberglass curling over the top and bottom pieces of the mold, meaning it's impossible to remove those pieces without dremeling. And then also the mold cannot be removed without completely destroying it. So we need to figure out ways to fix all these things.
So as mentioned, the tail cone mold that we had previously was very successful. We got working mold. However, it definitely can be improved upon. One of those things, as you can see on the top and bottom, we added more ridges because on the original tail cone, it was not very sturdy when we added the fiberglass in there. So we added some ridges on the top and bottom to keep it more sturdy while replacing the fiberglass in there. We also made the top and bottom, we extruded a little more because in the previous slide where the fiberglass was sticking up over it, we don't want that happening again. So we lengthened that so that the fiberglass is fully in the tail cone mold. And since we originally put vacuum tape over the screws to prevent them from poking through the bags, that didn't work very well, so we're going to need to design caps for those. We also need a lot more mold release. Epoxy ended up getting everywhere in every seam possible, so we have to put a lot more mold release on the whole thing so that anywhere the two parts are touching, we're going to add mold release. And a decent amount of excess was required to for the fraying, so that can also be improved by better handling. And yeah.
Go back a few slides and just mention one thing that I think could be elaborated on a little bit. For this integration part, where it says that it's a modified ogive, Devin did explain that it is starting with about ½ an inch of a cylindrical start rather than that ogive shape. That is because the way that we are doing tail cone integration, or at least currently planning on doing tail cone integration, is a little bit different than previous years, just because it worked out differently this time with the way that Structures has designed their stuff, so that integration has to be done kind of very last minute, and things don't quite fit as well or fit as easily as in previous years. So we are planning on radial bolting the tail cone rather than epoxying it to the to the motor retainer, which means that the motor retainer now needs to have a slightly taller lip on it for our tail cone to attach to. So the conical start of the modified ogive just means that it would actually like fit onto, it wouldn't start to curve inward and be kind of impossible to fit onto that lip without it kind of warping the tail cone, because the tail cone is a little bit less sturdy even when it's at the same thickness as the body tubes. It is going to be a little bit less sturdy than the body tube, so it is liable to warp. We could probably force it on, but that's not a great idea. So it's kind of a balance between ideally that conical start is a little bit smaller than the height of that lip. Currently, I don't know how set in stone this is, but that lip last I heard was planned to be about 3/4 of an inch potentially. So 1/2 an inch is kind of just a current estimate of what will probably work well, where the ogive can kind of start to curve in, just to basically have the most ogive length as possible without essentially the conical start to this is, or the cylindrical start to this, sorry, is essentially just extending the body tube length and doing that as little as possible is kind of the plan here. So it's about kind of a balance between that. All right. And then just the last little bit, future plans, kind of the things that are more at the front of our mind going into C term after winter break. Finalizing the modified ogive design with structures. Like I said, those numbers are not set in stone right now. So working with structures and just figuring out whether or not we definitely are going with the modified ogive, and if so, kind of the exact dimensions for that. Also, we are at a phase where once we decide on our final tail cone design, we're pretty confident that we can manufacture one and have it come out like worthy to actually be used on the final rocket. So any future like tail cone practices could potentially be the final tail cone, essentially, is how that's going for us right now. And then completing a successful set of practices for fillets, and for layups. I've merged those words together, just to get those processes down and see if there's any more changes we want to make. Again, coupon analysis, and then testing, because we completely overhaul our bevel jig. We have no idea how that design actually works realistically. So actually testing that with just laser cut wooden fins for now for convenience. And then currently we're also waiting on respirator health checks because EHS is a little bit complicated this year. So as soon as we can get those done, squaring tubes.
Heard about like the different service standard.
I do see what you're bringing up. I'll be honest, I've not given that too much thought. I would not say I'm super concerned about that. The bevel jig will be sliding back and forth in a way where it's not the same parts aren't touching the same part of the disc sander itself the entire time. It won't be sliding so much that every part of the fin touches every part of the disc sander. So some, like the middle parts, will probably get a lot more of that higher velocity, or sorry, lower velocity. But I don't foresee that being a major issue, just off the top of my head.
Where's the circular saw?
I think that was, I think what we meant to say was disc sander. I heard that too. Disc sander was, yeah. Yes, it's on the side of the belt sander. Yeah. It's a lot more stable. The belt sander likes to just kind of move around even when you lock it in place. So this eliminates that.
Okay, and then the.
Oh, you mean the one that got completely, absolutely shattered by me? Yeah. But that was actually, I assumed that was from like some design error or some error just where like the individual, like the 3D print was not a great quality. So it didn't have like right angles. It had a lot of just like slight curves. And the parts where there should be right angle, it was a lot of pieces beating kind of like this. I assumed we got epoxy like on those and that kind of made it hard, or maybe our mold release failed. It was entirely just because every surface that like interfaced with another surface got completely covered in just a thin layer of epoxy. So hypothetically, mold release should fix that. I know the biggest issue in past years with this design was getting it so that the screws didn't epoxy themselves in, and that actually was not a problem for us. So optimistic, I think. Yeah. Okay.
So not too much, I think it does hinder how the power lines are used.
Yeah.
When epoxy trying to do it, so.
Yeah, I read the specific instructions that the mold release wants you to do, and have not done it entirely like that. Kind of did like half of what it wanted, where it's just like one layer and then you wipe it off, and then another layer and then you wipe it off. So there shouldn't be like a buildup, is what I'm saying.
Okay.
It was very, very hard to get out. Part of that was because nobody knew why it was stuck together. So it was kind of hard to figure out how to get it apart. But reusing a mold would be nice in case you're in a situation in future years where you're just starting to do practices and you can not have to, every time you do a practice, reprint a mold. So like I said, ideally in a perfect world, we only make one more mold this year and then we perfectly nail our tail cone and that's it. But for future years, just being able to reuse the same mold during practices. Right.
From shoulders to dogs. Do you wear wings? No, no. How do you wear wings? No, I have not. Do you wear wings? It's so good. Isn't that a great video? I can feel. So now you understand. Which ones? No, they're okay. They're still. They're closed now. They can't see them. Those questions are closed now.
Yeah, okay.
Looks like you spent your day. Also, I'm asking you because I don't know about. Are you on my? I'm going to say something. So there is. Why would I be on your side? I be on your side. There were multiple times where a message has been sent to the channel that I never sent. It came from my account. There's a message from EnP that just said no. And I did not send it. You definitely did. I don't know. I don't have access. Well, how much did you have to drink? I absolutely did not react to the reactions for these popular. I didn't know that existed. Anyone have access? Well, so no. Basically, I will go in. Those that shit goes to the meats. I do not have your side. I know. I'm so confused. I didn't say don't know what's It's not harsh. Not hard to do that.
You get notes? Oh.
Yeah.
Oh my God.
You get some great
You
notes.
reacted, Nick, and then I reacted. I didn't do that.
You have my cell phone?
No, I didn't.
Guys, you can't fumble the name part.
I don't like where would you did.
Oh, it is.
My account.
Should we live?
Doing things that's hidden now. I can't.
Put your name and they'll take their name. My name's Josh. Yeah. I'm Josh.
How could I come back?
It's all Josh.
All Josh.
Yep. Sure.
We're missing Josh, you know, the most important.
The other Josh.
Legs with people. Yeah, just like that. And the center.
You like to be in the table.
In the table? In the
How could they not? Big smiles can you love HPRC, right?
They will.
You guys still have a couple.
Oh.
Oh, you guys are recording? Oh, wait, you didn't record. Why didn't you record?
You guys are up here. Do you want to start with you or do you want to start?
Do you guys want to?
You guys have started?
Man, I don't mind getting over with.
I'm good at. Just the one.
I gotta get that.
Just.
No.
Yeah, I can't even say imagine everyone naked. I'm making nervous. Like, what are you laughing at? How I can't tell. You understand?
Where's the one line? I don't have proof.
Yeah, so,
God dang.
yeah, but I don't know. It's pretty.
You better not be recording this.
They are.
They got the presentation. Wait. I'm pretty sure people enjoy it. So I watch you guys from somewhere. You know? We're always being like
Everyone else.
Yeah, but I got the seat.
Keep the seat.
Like,
Keep the seat.
you know, I think I'm just.
But I think people want to see the suit. So you guys stand up.
I can just like jump.
I'd love to see you on one day.
What? The stool's being taken. Bro, it is not a safe stool. Yo, I'm on the table on this.
Dude, this is the worst presentation ever. We're actually talking.
Oh, wait.
Oh, we're.
Photo again.
You get it on.
Yeah.
On the average. Sorry, I can't say that. Is this recording?
Is this me recording? No, say it on the mic.
So it doesn't follow through.
I'll reenact it. Put that in.
You reenact it. Performing the massive rocket.
I can do that. Wait, no, we're a team, so you see.
Oh, everyone together.
I got one.
All right.
Yep. Ready.
Okay.
Hi, we are two-stage structures, and this is our CER presentation. My name is Josh.
My name is Ryan.
My name is Matthew.
I'm Nate.
I'm Jack.
I'm Anthony.
So a little bit of an overview of what we're making this year. We have three different subsystems. We have the rocket coupling, which seals the avionics bay. It's going to hold the air brake system and the recovery bay. We have the payload couplings, which mount the payload parts. And then we have the motor retainer, which is mounting for the motor and holds it in the rocket. All of our parts were designed around a factor of safety of 1.5, which is industry standard. And we accounted for tolerances in machining, which is what the knockdown factor of 1.5 is. And then an environmental factor of 1.1, because some of the test launches are at colder areas than when we go compete. So the first system is the rocket coupling. And for our general rocket design, because we have two different ones, we kind of followed a similar design for both. This involves having two different size bulkheads that are mounted
one that is inside the rocket and which is the upper bulkhead, which is smaller and is a load bearing bulkhead. And that mounts to the smaller or larger flange on the rocket coupling. And the lower bulkhead is larger and is surface mounted, and they have two separate clocking features, which we will go inside.
All right, so for the sustainer part, so most of our coupling designs are based on last year's a little bit. The only difference is for the actual rocket coupling design right here, we decided to do a little bit of an experiment. So we have it as a single coupling versus a two coupling design that are clocking together. So in this case, we still have some clocking features, but not for the reasons that they were there last year. So on the upper part, which is the smaller radius for the bulkhead, we have a 1/16 inch screw. Mainly, most of this is just for a visual design to know which side is the top, which one's the bottom. So that way the bulkhead is going to be put on top and on the bottom, like no matter what. So nothing changes, especially if we're putting more parts like on top of it. And yeah, so in the sustainer part, sorry, these two parts. Oh, sorry. There we go. Okay, so the sustainer part is located on the main rocket. So we have two of them. So these two is just going to be the 5-inch around the rocket. That's about it. That's the only difference compared to the next part, which is the booster coupling. Here, this is located on the booster part. This one's the only one that's different in diameter. This one's going to be 6 inches. And again, we're sticking with the single coupling design to try and experiment to see if it would work. We haven't manufactured any of the couplings yet, but we have been focusing a lot on the calculations to make sure it works and is in the right field. As you can see in some of these designs, they have 9 radiables. So it kind of goes around. If you look at it from like a top and bottom section, you have 9 going around, and then the second part, another 9. So you have 18 radiables total, versus just using epoxy to kind of keep them together.
When we were doing the hand calculations for the rocket, we focused mostly on the coupling walls and tabs. For the bending moment, we decided that it would make the most sense to use the max bending moment from the 30K rocket because we wanted to ensure that it would not fail when the rocket ended up reaching higher altitudes in the future. For our calculations, we focused on the recovery and bending loads. The tabs undergo the recovery loads with shear stress and bending stress. And the coupling walls experience bending momentum with hoop stress, which is the tube breaking from bending, bearing stress, the holes deforming from bending, tear out, which would be the materials shearing if the bolt doesn't break, and then bolt stress if the material breaks, but if the material doesn't break, but the bolts snap.
Okay, so a lot of B-term we spent doing calculations mainly. A lot of Mitch, me, and Josh have spent a couple grueling hours going over because we mainly wanted to understand how they were working. So we have a few diagrams that we were looking at. A good reference book that we looked at was a Roark's formula book about stress and strain. We kind of went through it here and there and tried to understand what the calculations were being used, like how they were being used last year. So a good example that we were looking at, like for hoop stress, we compared it to a Coke can. So we imagine it as a pressure force being pushed. And because it's a coupling, it's going to be like a pipe shape, which is where obviously the hoop stress would be most useful. So we tested not only on the walls, but we also tested on the tabs. So the tabs were the little pieces where the radiables are being placed where the bulkhead. So when the bulkhead's being placed, they're being screwed in at those tabs. Those were the most concerning parts, especially for our single coupling design. Because now that the bulkhead was not going to be rested upon just those radiables alone. So we really were focused on that a lot, which is where we have the tabs over on the margin side on the left. Obviously, the highlighted parts we have here are the most important ones. So we have bearing and tear out. Bearing is obviously going to be focused along those where the radiables are located, because they're going to push against the coupling itself And we want to make sure that works, because if not, then the whole coupling completely falls apart, because the bulkhead is going to fall and we're going to lose holes. And then we also tested the tear out, which again, more diagrams as the rocket goes up, the forces pushed against the variables might cause like a little small distance where it was originally. We want to be careful with that in case the variables like fall out over time, because we are going to keep replacing. Like if we want to keep replacing the coupling from the body tube, we have to be careful that we're not messing around with the fiberglass on the body tube. And so, oh, did I not this? Oh, so yeah, the calculations were pretty similar to both coupling designs, the sustainer and the booster. Yeah, there's not much else to really say about that. The airframe, which is the body tube, is going to be a lot weaker than the aluminum. So we will have to focus a lot on the actual physical tests and rather than relying on the calculations that we did.
Okay, so we did a structural simulation to just confirm anything that we got for hand calculations and make sure we didn't miss anything. So this is a simulation of the maximum force by parachute deployment. So it's applied to an area around the smaller like shelf area of that bulkhead gets attached to. So that's where the force is applied to. There's a fixed support on the outer walls of this. And so our results for this were that the maximum von Mises stress is 1.98 kilo PSI. And so this is much lower than the strength of the yield stress of the aluminum. So that gives us a factor of safety of 21.09. So yeah.
And then this is the payload couplings. They are pretty similar to last year's design. However, we still have, we have made some slight changes and we do have calculations to go with them.
So to start, the nose cone coupling will be epoxy to the body tube and we'll use spring pins instead of using screws. This is because it doesn't really need to be detached while it's in flight. So we can just use the spring pins and epoxy. And the payload recovery coupling that's actually connecting to the body is going to use radial bolts, as I said before, because it's in the middle and it's much harder to epoxy there. And as you can see with the gasket, we're going to be laser cutting that. And this allows it so that we can quickly try different ones really quickly and see what works. And yeah, and then we're going to use a feature to hold the gasket in the bulkhead for the couplings in place.
And then we're going over the loads that we will be, or the coupling will be experiencing. It will experience epoxy shear where the coupling might be ripped out from the recovery forces as it comes down. There's bolt shear, making sure that the bolts are not ripping against the cut or shearing against the coupling forces that it is experiencing from the rocket. And then there's full tear out or simple and complex tear out, where the simple tear out just focuses on the shear and the complex tear out focuses on the tensile and the shear stress that it experiences. And then these are the calculations that we have gone over. The epoxy or the bolt shear and the complex tear out are the most important because we do not want our bolts ripping off of the rocket or our couplings. And the calculations have been done well, and we are close to our factor of safety and making sure that we're well within range.
So we did a stress simulation of the payload couplings, and here we added
a finer mesh around the fillets of the payload coupling, which is when we machine, there's going to be a small radius that we want to account for when we do our stress simulation. We found that our aluminum has a max yield strength of about 40K PSI, and we found that the recovery force would be about 100 pounds force. And we found the lowest factor of safety of this part is 110 with a maximum yield strength of 2.5 to the 6. The next part is the motor retainer part, and that will hold the rocket motor inside the rocket. And we will go over that in the next slide.
Okay, so the motor retainer is going to remain mostly consistent with last year's, except because of the diameter change, we're going to increase the top part to 6 inches, whereas the bottom part is going to remain at 5 inches. So there's going to be a lip near the bottom part of the motor retainer that's going to, it allows the body tube to slide down and sit on the lip. And then that is going to be secured by 8 spring pins. And then the motor is actually going to be secured with 12 bolts. And there you get a cross-sectional view of it. And yeah, so the bolts are going to be about 0.136 inches. And then, yeah.
So we also went over the load cases for the motor retainer, and we expect we know that there's going to be a recovery load on the motor retainer that is pointing down in this sketch, and then thrust forces from the motor itself that are pointing up. We know that the bearing failure is going to happen probably before the material actually fails, and so we want to focus on the spring pin holes as well as the screw holes that mount the part into our thrust coupling. We also want to look at tear out for the spring pins to make sure that they won't tear in flight, and as well as the epoxy itself to make sure that we don't have any failing as the motor is in the air.
So this is actually one of the other important calculations that we had to do, because last year's Excel sheet was a little all over the place. So what we decided to do was organize it a little bit more, and we added in the notes section of our Excel sheet the equations that we actually had to use. And then we also kind of added additional like parameters that we need to know, just in case. And so just like I was stating earlier, we still have the margins that were included of our factor of safety, including all of our other values. And so going back, so instead of using the so in this case, we're focusing on the body tube and the coupling itself. So we did both calculations on that end. So that's where the bending, the bearing stress is at, and as well as the pin bending, because that's where they're going to be attached to each other. And then the lip bending, that's again another important part. So because we're switching to bigger spring pins this year, we wanted to make sure that the FOS were still within a reasonable range. So that's what we did.
We also did a stress simulation for this part. We had a finer mesh around the edges of and corners of the thrust coupling. We also looked at the factor of safety and found the lowest factor of safety on the thrust coupling using the thrust force as our force pointing up was 34.56. And we found that the maximum part stress was 1.5K. And yeah, thank you guys. Is there any questions? Yeah.
That's a factor of safety of 110.
Yeah, it's something that we want to review. We use the recovery force of 100 pounds force, and that's what I got, but I definitely want to go over that again because that does seem very high.
I just want to say, can you actually go to the slide right now?
Yeah.
There isn't any margin. It's like it's close.
Yeah.
Like 2 weeks, like I.
What we got last week. It's radio once a bit. we'll experience something. So you say it's also going slow. So
My question is, does it to be designed?
it's more. So. Last year we had.
Yeah, so these are all fire safety numbers.
So these are like margins, so it's how far away we are from the factor of safety.
Way more which isn't necessarily a bad thing.
Yeah,
It's just a lot more than that.
yeah, we can definitely look into reducing material. Yeah.
Okay, okay, the other one is slide 131. And it's, I just wanted to make sure, so in the previous slide you talked about, you have an upper clocking feature and a lower clocking feature. Historically, when we put couplings on either side of the avionics bay, we seal it off like that. We do the couplings that are in like opposite rotation. But I just wanted to clarify that these are the upper and lower sides are the same for both couplings. And if that is the case, they have a different clocking feature on the top versus the bottom. And does the avionics, is that everyone aware of that? It's different.
Yeah, so we have a clocking feature on the top and the bottom that are separate, but the actual like sealing is going to be the same.
Okay,
with the
so that's,
test.
sorry, that's a really big question. The question is, so since the upper clocking feature is
Mhm.
different from the lower clocking feature.
Right.
Historically, the lower coupling versus the upper coupling, and then the upper one is backwards.
Oh,
So that
okay.
both sides are interfacing with the same part of the coupling.
Mhm.
So I just want to clarify that that's not the case here, which means that the avionics bay is interfacing with two different types of clocking features because the couplings are faced in the same orientation. Is that correct?
Yeah, we have to double check with airbrakes because they're kind of making some changes to how they want the coupling to be designed. And so when we add those changes, it might change how the coupling's oriented in the rocket.
Okay, I just want to make sure that in terms of interfacing and integration, you know, everyone knows what they're actually integrating.
Yeah,
It's different.
yeah, that definitely makes sense.
Make sure you guys be better. It's that, 1/16 inch we have, the. Spearhead don't intersect.
Oh, yeah.
The spearhead is like a lot more even than the whole.
Right.
The larger town, so. I have to move that. Just to make it mild, just because of anything. It might not be, I don't know, something maybe I should probably.
I think on that side, the screw head is like going the opposite direction, so there's no head there.
Yeah.
But it still might be something to think about.
Okay, yeah, I know. Well, no, it's on the inner one.
Oh, yeah, correct. So,
So
yeah, we would have to
Yeah.
interface with the head, yeah.
Some scratchy feel. But it's something you find. You notice like something. Sorry, I have to make that. What is the reason why highlighting the top shear? It's called the top bending.
Yeah, so we just wanted, or I guess we're worried about both essentially, but yeah, the bending is probably more important to look at just because of how the gravity force is pushing on that.
Yeah,
tabs.
bending's gonna fail before the shear does.
Right, yeah.
In this case, like, what the.
Mhm.
And then Okay, next thing, I can see this, that's fine. I'm just letting you guys know, it's also why the fact is, I think for that part, all their simulations, keep go to the next. Yeah, it's cool. Okay, so some notes. But when you guys are doing courses and pictures, make sure that actually put on the course and pictures. For instance, like the books right now, it's just being applied. Well, actually, no, it's like on the spot. But the pictures right now are just on the entire surface.
Right.
That would be the case if we epoxied it, but because they're being radial today, like
Gotcha.
things on the entire surface.
Mhm.
So whether that's putting in split lines around all the screws or doing just the actual internal surface screws.
Gotcha.
That is going to increase scratch safety on all these parts, just apparently, it's just basically fixing a lot.
Right, it's more rigid.
Then as well, another part that you fix is whatever surface is being supported by the body tube. So like that lip that goes around the outside is going to be actually like being pushed up on from the body tube. So that's also good. Just keep that in mind. And that goes for all the simulations here. Yeah. And then for the epoxy joints on 139, I do think we should do a physical test. I mean, like, we run the epoxy joint every year, but like, I'm just paranoid about it now. So we'll look into doing that in the future. But
Yeah,
make sure
sounds good.
it's on your radar. Try to do some sort of epoxy test of that. Whether that's even just like mixing the epoxy, throwing on some spare. We have spare.
Right.
Badly, but they still are that stuff. Whether it's doing something like that, or something else, that's yeah, just like keep mind that one. And then yeah, just the pictures of simulations are, I think, gonna be a lot more.
Yeah, we can make those changes and rerun and make sure it matches our calculations. No, we're still using the same. It's a little hard to see in this photo, but it's the same. Okay, yeah. Thank you.
Okay, I don't want to do it. I don't know. No, yeah, okay. I agree. You should be. I was, just, I had some. And I was there. I don't call up there. You might figure out who's on my.
No, like someone else on your, someone's on your Outlook.
No, there is one message and one reaction. There's more, who's complained about the contract?
I'm really talking about. I'm just going to.
I'm not doing this here yet.
You see the chili?
Yes.
The chili. No, make the HPRC.
Well, I got chili. No. I ate non-those. I don't just yeah.
But by the time everything is facing down, like, yeah.
Yeah, so I'm like doing. Like, that was on the camera. Yeah, it's like we were.
small. It's like a little bit more. Yeah, it's like. Back to like. Two hat, yours like two hats. I'll be take one step sensor. There we go. Now smile like you guys see.
Or swear guys. Oh yeah, that's bad about what he does with that. Well, I've seen my man does with that. Bill, you have not seen that. One of them, I don't know what. I didn't know AI was allowed to do
Reminds me of like the Steam, the Epic Games CEO being like, the company shouldn't have to include, named AI on their thing. It's like,
Yeah.
And then Steve's like, yeah, I'm just gonna do it anyway. The consumer deserves to know.
You guys so ready?
Yeah, bro. So ready. Yo, birthday CDR. Said what?
See watching in silence says, wow, I'm looking at it.
Bro, I think.
Wait, who? Ethan?
Yeah, the big one.
Yo, what up, Ethan?
What's up, Ethan? Say hi to Matt Frank for me.
Yeah.
Matt Frank.
A little bit.
Are we all?
Yeah, cool.
Shout out to Ethan and Matt Frank.
Center, and yeah. Oh, okay. Well, here, let's see. When can you stop seeing my hand?
I'm gonna make it bigger so it's good.
Like, how zoomed in is this camera? I feel like it's in my face.
Here.
Yeah, keep moving.
We do like.
Imagine it's like a fisheye lens.
Okay, so I got this. We got this. We're good.
See, right up until the side shoulder.
Okay, cool. We're good.
Oh, I can see. It's like pan.
It's a fisheye. It's a fisheye lens. Yeah.
Dude, just like Ethan.
What's Ethan saying the Slack now?
He was.
What is he saying? What? What's he? Sean, I heard that straight. He said.
Not straight, it's deserved already.
Yeah, I think which shot
just two thirds.
Yeah.
Start presenting.
You are ready. I don't know if that's ready.
It's 7:59. We got less than a minute.
In case anyone else shows up.
Yeah.
Are the balloons on right now?
Yeah, it's zero.
Are we playing? Oh. Is that like a
Montgomery. He's kind of watching like
he had the best season of all time, then was a first round exit, and then it's just never.
He's like kind of like a peak last year, and they need to rebuild it.
We're ready to start. All right, we're at two-stage rocket recovery system. I'm Sean.
I'm Dylan. I'm Taha.
I'm Tice.
All right, so quick timeline. We've been through A term. Now in B term, we've gone through our CAD. We've done PDR. So now for CDR, then we've added in wiring diagrams, providing the CAD. Next term, looking forward, then we'll make a prototype sled, test out the printing, do parachute folding, and then hopefully there's a February launch that we can do some injection testing and then make some technical documentation. So same as PDR, quick overview. Our sustainer will be dual end, dual deploy. We have the drogue that's 36-inch diameter that will deploy at apogee. We have the main that's 96 diameter that will deploy near 1,000 feet. And then our booster is the single parachute that's now 60-inch diameter, which is a change from PDR. We will still be using black powder to separate, and we will have redundant altimeters to trigger them.
All right, so these are our parachute requirements. So the drogue will deploy at near apogee. The descent rate has to be between 65 and 131 feet per second. The main parachute will deploy at or below 1,500 feet. That is, the descent rate at landing will be less than 36 feet per second. The booster deploy at or near apogee and it'll have a descent rate at landing of less than 36 feet per second. And that in the current parachute specs, the drogue deploys at apogee, which is around 6,760 feet. The descent rate under drogue is about 65.42 feet per second. The main will deploy at 980 feet, and the descent rate at landing is about 16.21 feet per second. The booster deploy at apogee, which is 3,220 feet, and the descent rate at landing is about 20.96 feet per second. So all of these requirements are met by current parachute specs. The main parachute is a 96-inch toroidal parachute with a descent rate of 16.21 feet per second, an opening force of 97.51 pound force, an opening time of 1.97 seconds. It weighs 25 ounces, and the packing dimensions are 4.9 inches by 7.4 inches. That was the same as PDR as well. This is the drogue parachute. Now, it was changed from a toroidal to an elliptical because the toroidal actually worked too well and did not have a fast enough descent rate. So this is a 36-inch elliptical parachute with a descent rate of 65.42 feet per second, an opening force of 18.31 pound force, an opening time of about 0.19 seconds. It weighs 4.5 ounces, and the packing dimensions are 2.6 by 4 inches. The booster parachute, this is a 60-inch main parachute. This is our 60-inch main parachute. It is toroidal. It has been increased in size to meet the IREC descent under main requirement. It has a direct descent rate of 20.96 feet per second, an opening force of 59.29 pound force, an opening time of a second. It weighs 10.9 ounces, and the packing dimensions are 3.9 inches by 5.1 inches.
And to pack the parachutes, then we'll be wrapping them in a Nomex blanket. Because we're doing pyrogenics, then we need to have a fire retardant material to protect our parachutes from friction and from the charging. So we'll need 3 blankets, one for the drogue, which is smaller. It's like an 18 by 18 to work. And then for the booster and the main, then we're looking at 24 by 24 inch Nomex blanket. But with how tight of a fit the packing of the sustainer main is right now, then we'll have to do folding tests to see how tight we can pack it and see if a 24 by 24 inch Nomex blanket will still fit in the airframe. So our avionics requirements, still the same from PDR. We have to have completely independent and redundant recovery system, at least one redundant system in each part. I must use a cost flight computer. We have to be either lithium coin cell or alkaline batteries, but LiPo or band. So that affects the tele-GPS. And then the energetic devices have to have shunted leads or igniters, which is what the screw switch is for.
So this is going to look very similar to what we had at PDR. This is our primary altimeter. It is the Blue Raven, manufacturer of featherweight altimeters. It was used in past years, so it's already proven. Screw mounted, which is easy for CADing purposes to build the mounts and just screw it right on. It's got multiple sensors, different ways, accelerometer, barometer, and gyroscope to help measure altitude accurately. The max altitude, as you can see, is 45,000 feet, which is much higher than apogee of about 5,700, so we should be good there. 4 channels, so you can dual deploy, which is perfect as it's going to need to deploy 2 parachutes. And then also the battery variety is very large, which is good, so we can make sure we get a battery that works properly. The secondary altimeter is the RRC3+. Oh, also both of these altimeters are off the shelf, so we meet that requirement. This is MissileWorks altimeter, again, screw mounted. This one only has a barometer, but the max altitude is 100,000 feet, again, much higher than the apogee, so should be good. This is 3 channels, which is, again, more than enough to dual deploy, and the same wide variety of battery range, voltage range. Here are the wiring diagrams. This is the sustainer. So on the left is the blue Raven side. So you can see the battery board with the screw switch connected to the blue Raven, which sends one channel up to the primary main parachute and one channel down to the primary drogue parachute. And on the right is the RRC3 Plus, and you can see the tele-GPS there as well. And those are also connected to the battery switchboard. And again, it sends one channel up, one channel down to either parachute. And you can see that we have 2 charges on the top and bottom for primary and redundant. Here's the wiring diagram of the booster. Again, it's pretty much the same, but just put into a tighter space. The battery board connects to the altimeters, which goes up through and connects to the charges. And then you have the 2 charges for this one. The only difference is one will go to the parachute and one is to the separation charge. So this only has a 1 parachute, but still 2 charges, 1 at each end.
All right, and here's the sled system that will be housing all of these avionics. So here is the sustainer bay. This one is dual and dual deploy, so like parachutes attached at both ends of this bay. It's 13 inches in length and it has 1/4 inch threaded through rods. It will be housing the Blue Raven and the RRC3 Plus, and will be made out of G10 fiberglass bulkhead, which has a outer diameter of 4.88 inches and an inner diameter of 4.85. So, all right, and anyways, and on your left-hand side, you could see the RC3 Plus altimeter and the tele-GPS installed onto that sled, and spacers all together. And there's the battery board as well, and the 8-gram charge well at the end. On the other side, that's where the Blue Raven will be housed alongside the altimeter battery board. And then there's the eye bolt as well. And then as for the other bay, the booster recovery bay, this one is just single end deploy, so just parachute attached to one end instead of both. It's 4 inches in length, has 1/4 inch threaded through rods, also be housing the Blue Raven and the RC3 Plus, also made out of G10 fiberglass bulkhead. This time the outer diameter is 5.8 inches, but on the lower end, it's like the lower end is larger and the upper bulkhead, it's smaller, only 4.9 inches in outer diameter size. And the mounting holes on the upper bulkhead, there's 4 holes, each of which is 0.136 inches in diameter, which means you just need a number 8 size screw. And for the diagram, so you can see the terminal blocks right next to the deploy end, and then have the Blue Raven on the left side alongside the battery board. On the other side, there's the RC3 Plus altimeter alongside with its battery board. On the other end, you have your 8 grams charge well, the separation, and then on top you have the one for the parachute.
All right, so for the booster, then our upper bulkhead will interface with structures. So in their presentation last, then you saw it mounted, the bulkhead mounted underneath the tabs. Here, then you see it mounted above. Either one will work with our bulkhead. It's small enough to be able to fit through the smaller tab holes. If it needs to be mounted underneath, it can get on the inside. Again, there's 2 charge wells for the separations because separations will be on the other side of this coupling. So there's 2 charge wells for redundancy. And then there are the 4 size 8 screw holes that are used to mount for the 4 tabs that they have on the coupling. So for the simulations on our bulkheads, then we used a von Mises stress simulation, which it's not great for bulkheads because, or at least for fiberglass bulkheads, because fiberglass is a composite and von Mises is for like a ductile metal. It doesn't really take into account a composite's material properties. So for this, then we assumed, or we didn't assume, we pulled from the laminated plastics company's data sheet the crosswise tensile yield strength, because composites are weaker in their crosswise direction than in their fiber direction. So this is where it is going to fail first. So these bulkheads basically
it would first fail at 38,000 PSI. The max that stress that it will experience is not even 8,000 PSI. So basically, it's not failing. Same thing was done with the drogue, and then again, you'll see with the booster. Again, if ANSYS could do a Sci-Woo or Sci-Hill simulation, then that would have been better for a composite material, but you have to do like a special, have a special version of ANSYS, and I was not doing all that. So we went with the von Weisses. So yeah, it's not failing. Looking forward, then we'll have more interfacing meetings with structures, but hopefully this time though it will be with separations too. We had 2 meetings with structures to get like, the basic mounting idea, but as we move forward and as the 3 of us work together, then things will probably change. So that's the biggest item on the agenda. We'll have parachute folding so that we can determine that final Nomex blanket sizing, because again, right now then our main sustainer parachute folds packs at a 4.9-inch diameter, and it's a 5-inch diameter body tube. So we need to make sure that we can get that as tight as possible. Print a prototype sled and practice assembly, and then measure shroud lines, because right now then our lines are we haven't measured the shroud lines yet, so they're not really too accurate. So we'll have to update those, and then do vacuum chamber altimeter testing, which hopefully we'll have a working vacuum chamber by the time we need to do that. And ejection charge testing if there's a launch in February. Any questions? So this then, I always show it in the orientation for when it's like descending under a parachute, but that smaller one is the upper bulkhead. So it's flipped when it's sitting in the rocket, but this is when it's under descent, the way it's oriented. And I just, out of habit, then I always put in the way it's under descent. We have not. I'm not sure what payload we'll choose for their color, because we don't want the same colors. But since we have 3 parachutes, then pretty much whatever color payload doesn't take, then we'll take every other available color. With pink shroud line, pink.
I'll vouch for pink.
Just to put this out there regarding parachutes.
It's visible.
I don't know. No idea. I have absolutely no idea if this is happening. And there was talk of I don't want to go into too much detail just because it's a long story.
Oh no.
Mo may have a contact with someone who can maybe make us parachutes. But that fell through. Oh, did it? Never mind then.
Actually, I do have a question about parachutes, which is, have we figured out, now that we know exactly which ones we want, where we're ordering them from? Because if we're ordering them, if we're gonna order a parachute from Bangkok, we're getting them. That's it. Another question, have we considered a new altimeter? This isn't necessarily something you guys need to worry about right now, but the Blue Raven goes to 45K, and we're hoping to go to 45K next year.
There's a problem with next year, if we go to 45K, then the RRC3 Plus only has the 3 ports for separations. Then or for the 2 states, it's going to need more, because there's going to be a booster, there's a drogue, a main, and a separations. So even though that meets the altitude requirement, it doesn't meet the port requirement. So we could do another altimeter, but then we need to find another altimeter for that still. So there's next year, then there will be, we can either look into that now, or though we have identified those problems, I just don't know if we want to solve it now, or you save it for next year.
Two brand new altimeters next year. it might be a good idea to hold that and maybe. Not really. But also on side 162. Have we considered?
It's low.
Yeah,
It's got a second.
Oh, perfect jump.
How about that?
Over the gap. So that's not something that we've looked into yet. We can just 3D print a piece that will go like over the like that will close the gap as a bridge, or we can like run it up the spacer and zip tie it around the spacer, since there's space between where the coupler tube will be and where the edge of that spacer is, so the wire won't be like crammed in there. We right now then we have terminal blocks in there because I figured that it would be easy enough that we don't really need the Wagos. But we might, especially where right now then we're running into some questions with the booster for like order of construction, then we might using Wagos might help make it a little bit easier for that part. So we might have to look into that for the booster.
Anybody else have any questions?
There's one question.
Oh. No, it just kind of happened this way. Like we wanted the batteries for each part with that part, so it ended up being that one side had very little. There was a plan to put a camera over like where the separation would happen, so most likely the camera will go with the other altimeter and it will close up that space. But we're planning to use the same camera that 30K uses, like the same cheaper model. And so once that gets solidified, then we'll have what to throw in there. Anyone else?